Tonight, we're going to explore something that will fundamentally change how you understand the stars above you. We're going to discover the hidden choreography of binary star systems, not just the basic idea that two stars can orbit each other, but the profound physics, the intricate dynamics, and the cosmic consequences that flow from this celestial partnership. By the end of this journey, you're going to understand structures so complex and beautiful that they challenge our very notions of what a star system can be. Before we begin, if you enjoy these deep explorations of the cosmos, a quick like or subscribe would really help the channel grow. Now let's begin our journey into the realm of stellar pairs. Let's start with something remarkable. Look up at the night sky on a clear evening. Every point of light you see represents a sun, potentially with its own family of planets. But here's what most people don't realize. The majority of those stars are not alone. They have companions, partners locked in an eternal gravitational dance. Most stars in our galaxy exist in binary or multiple star systems. The solitary sun we orbit is actually the exception, not the rule. This discovery came slowly to humanity. For thousands of years, we assumed every star was single, isolated in the vastness of space. Ancient astronomers saw points of light and imagined each one as a distant counterpart to our sun. The idea that stars could be paired together, orbiting each other across the darkness, would have seemed fantastical. Yet it's exactly what the universe has arranged. The first hints came in the 17th century. In 1617, an Italian astronomer named Benedetto Castelli was observing a star in the Big Dipper through one of the early telescopes. The star was Mizar, the second star from the end of the Dipper's handle. What Castelli saw startled him. Through the telescope's narrow field of view, Mizar wasn't a single point of light at all. It was two stars sitting close together in space. He brought this discovery to the attention of his colleague, Galileo Galilei, who confirmed it. Two stars, where the naked eye saw only one. For decades, astronomers debated what this meant. Were these stars truly together, bound by some invisible force? Or were they simply two unrelated stars that happened to lie along the same line of sight from Earth, creating an optical illusion of proximity? The debate raged because no one had any way to prove the connection. The stars didn't appear to move relative to each other. They just sat there, twin points of light separated by a small angular distance. Around 1650, the Italian astronomer Giovanni Battista Riccioli published the first detailed description of Mizar as a double star. His careful observations documented the positions and brightnesses of both components. Riccioli couldn't prove the stars were physically associated, but his measurements established that Mizar was worth watching. It became the first visual binary star known to science. The breakthrough came through patience and precision. Over decades and then centuries, astronomers meticulously measured the positions of suspected double stars. They recorded the angular separation between the components and the position angle, the direction from one star to the other. These measurements accumulated into long baseline observations spanning many years, and slowly patterns emerged. Some double stars showed no relative motion at all. The two stars maintained exactly the same angular separation and position angle over decades. These were optical doubles, chance alignments of unrelated stars at vastly different distances from Earth. But other double stars told a different story. The position angle changed. The separation varied, The stars were moving relative to each other, tracing out orbits through space. These were true binaries, gravitationally bound pairs. The astronomer who truly established the reality of binary stars was William Herschel. In 1782, he published a catalog of double stars, and over the following years, he continued observing them. By 1802, Herschel had accumulated enough measurements to prove that some doubles were indeed orbiting each other. He wrote that if two stars are situated very near each other and isolated from neighboring stars, they will form a separate system and remain united by the bond of their own mutual gravitation towards each other. He called such systems real double stars or binary sidereal systems. The term binary, meaning composed of two parts, entered astronomical vocabulary to describe these paired stars. Herschel's discovery opened a new chapter in astronomy. Here was direct proof that Newton's law of gravity operated beyond our solar system. The same force that kept planets orbiting the sun also governed stellar motions across the galaxy. Binary stars became laboratories for testing gravitational theory and for measuring stellar masses, tasks impossible with solitary stars. The implications rippled outward through astronomy. If stars could be paired, what did this say about star formation? About the structure of the galaxy? About the potential for planets in such systems? As telescopes improved throughout the 19th century, more and more binary stars emerged from what had seemed to be single points of light. Astronomers compiled catalogs containing thousands of double stars. Some of these pairs were tight, the stars separated by mere arc-seconds on the sky. Others were wide, the components separated by dozens or even hundreds of arc-seconds. The diversity was staggering. Some binaries had nearly identical stars. Others paired dramatically different stellar types, a bright giant with a faint dwarf, a hot blue star with a cool red companion. Then, in 1889, came another revolution. An astronomer examining the spectrum of Mizar A noticed something odd. The spectral lines, the dark absorption features that reveal a star's composition and temperature, appeared fuzzy and doubled. As the astronomer took more spectra over time, these lines shifted back and forth. The explanation was stunning. Mizar A itself was a binary, too close together to be separated visually, even through powerful telescopes. But as the two stars orbited each other, they alternately moved toward and away from Earth. The Doppler effect shifted their spectral lines, compressing the wavelengths when a star approached and stretching them when it receded. When both stars' light combined, the result was doubled spectral lines that oscillated back and forth with the orbital period. Mizar A became the first spectroscopic binary ever discovered, revealing an entirely new class of binary stars invisible to direct observation but detectable through careful spectroscopy. The 20th century brought even more methods for finding binaries. If a binary system happened to be oriented edge-on to our line of sight, the stars would periodically pass in front of each other, creating eclipses. These eclipsing binaries showed regular variations in brightness as one star blocked the light from its companion. Careful analysis of the light curves, the plots of brightness versus time, revealed the sizes of the stars, their temperatures, their orbital period, and even the shape of their orbits. Eclipsing binaries became powerful tools for measuring stellar parameters with remarkable precision. Astrometric binaries added another detection method. In these systems, one star is bright and easily visible, while its companion is too faint to detect directly. But the faint star's gravity pulls on the bright star, causing it to wobble slightly as it moves through space. Precise measurements of the bright star's position over years revealed this wobble, proving the existence of an unseen companion. This technique later became crucial for detecting planets around other stars, but it first proved itself on binary stars. Today we know that binary and multiple star systems are extraordinarily common. Roughly half of all Sun-like stars exist in binary or multiple systems. For more massive stars, the fraction is even higher. Perhaps 70 to 80% of massive stars have companions. The reasons for this high frequency lie in the star formation process itself, which we'll explore in detail. But the basic fact is clear. The universe favors stellar companionship. Our solitary sun is unusual, perhaps even rare, among stars of its mass and type. Let's understand the fundamental physics that governs binary stars. At the heart of every binary system is gravity, the same force Newton described in the 17th century and Einstein refined in the 20th. Gravity operates as an attractive force between masses. Every object with mass exerts gravitational attraction on every other object with mass. The strength of this attraction depends on the masses involved and the distance between them. Newton's law of universal gravitation states that the force is proportional to the product of the two masses and inversely proportional to the square of the distance separating them. In a binary star system, each star feels the gravitational pull of its companion. The force pulls them toward each other. But why don't they collide? The answer is motion. If the stars have velocities perpendicular to the line connecting them, those velocities provide what we call angular momentum. The angular momentum, combined with the gravitational attraction, results in orbital motion. Each star follows a curved path through space, perpetually falling toward its companion but moving sideways, fast enough that it never actually reaches it. The result is an orbit, a closed path that the star traces repeatedly. Here's something crucial that sets binary stars apart from planets orbiting a sun. In the solar system, the sun's mass vastly exceeds the mass of any planet. Jupiter, the most massive planet, contains less than 1,000th the sun's mass. This enormous mass difference means the sun barely moves in response to the planet's gravity. The sun sits essentially stationary at the center while the planets orbit around it. But in a binary star system, the two stars often have comparable masses. Neither can remain stationary. Both must orbit. The point they orbit around is called the barycenter, or the center of mass of the system. Imagine balancing a seesaw with two children of different weights. The fulcrum must be closer to the heavier child to achieve balance. The barycenter works the same way. It's the balance point of the two stars, located along the line connecting them, positioned closer to the more massive star. Both stars orbit this barycenter, completing their orbits in exactly the same period because they remain on opposite sides of the barycenter at all times. The mathematics of this arrangement flow from Newton's laws. The distance from each star to the barycenter is inversely proportional to that star's mass. If one star has twice the mass of the other, it orbits at half the distance from the barycenter. The barycenter itself moves through space in a straight line, following the system's overall velocity through the galaxy. If you could somehow see the barycenter marked in space, you'd watch both stars orbiting around this invisible point as it travels through the cosmos. Let's make this concrete with numbers. Imagine a binary system with two stars of equal mass, each containing one solar mass, the mass of our Sun. They orbit separated by 10 astronomical units, roughly the distance from the Sun to Saturn. The barycenter sits exactly halfway between them, at 5 astronomical units from each star. Each star traces a circular orbit with a radius of 5 astronomical units, and they complete their orbit in about 22 years. Now change the scenario, make one star twice as massive as the other, so we have a 2 solar mass star and a 1 solar mass star, still separated by 10 astronomical units. The barycenter now sits closer to the more massive star. Using the center of mass equation, we find the barycenter is located 3.3 astronomical units from the 2 solar mass star and 6.7 astronomical units from the 1 solar mass star. Both stars still complete their orbits in the same period, but the more massive star traces a smaller orbit, while the less massive star swings through a larger path. The orbital period, interestingly, is now shorter, around 13 years, because the increased total mass strengthens the gravitational forces holding the system together. These orbital periods are governed by Kepler's third law, originally discovered for planets, but equally valid for binary stars with an important modification. In its original form for planets, Kepler's third law stated that the square of a planet's orbital period is proportional to the cube of its average distance from the Sun. For binary stars, we must account for both stellar masses. The modified version states that the square of the orbital period is proportional to the cube of the separation between the stars, divided by the sum of their masses. This relationship provides a powerful tool. If we can measure the orbital period and the separation between the stars, we can calculate the total mass of the system. If we can additionally determine the individual orbits of each star around the barycenter, we can separate out the individual masses. This makes binary stars invaluable for astronomy, providing direct mass measurements that are extremely difficult to obtain for single stars. The orbits themselves can take various shapes. The simplest case is circular orbits, where each star maintains a constant distance from the barycenter as it moves through its orbital path. But most binary orbits are elliptical. Each star traces an ellipse, with the barycenter located at one of the 2 focal points of the ellipse. The degree of elongation of the ellipse is measured by the eccentricity. A circle has an eccentricity of 0. As the eccentricity increases toward 1, the ellipse becomes more and more elongated. At eccentricity 1, the ellipse becomes a parabola, no longer a closed orbit. Real binary orbits have eccentricities between 0 and 1, with some nearly circular and others highly elongated. The orbital eccentricity has profound effects on the binary system. In a highly eccentric orbit, the stars approach much closer together at periastron, the point of closest approach, than their average separation. Then they swing far apart at apastron, the point of greatest separation. This variation in separation changes the strength of gravitational interaction. At periastron, tidal forces can become significant, potentially affecting the star's shapes and internal structures. Gas can flow more easily between stars at periastron if they're close enough. Then at apastron, the stars are effectively isolated from each other, interacting only through long-range gravitational forces. Over the course of an orbit, the system cycles through these different regimes: creating complex and dynamic environments. There's a fascinating correlation between orbital period and eccentricity in observed binary systems. Close binaries, those with orbital periods of a few days or less, tend to have nearly circular orbits. Their eccentricities are very low, often essentially zero. Wider binaries with longer periods show a broader range of eccentricities, including many with highly elongated orbits. This pattern emerges from the physics of tidal interactions. When stars orbit close together, their mutual tidal forces act to circularize the orbit over time. Tides raised on each star by the companion's gravity create bulges. As the stars rotate, these bulges don't point exactly toward the companion due to the finite time needed for the star's material to respond to the tidal force. The misaligned bulges create torques that transfer energy and angular momentum between the star's rotations and the orbital motion. Over millions of years, this process damps out orbital eccentricity, driving the orbit toward a circle. In wide binaries where the stars are far apart, tidal forces are weak, and this circularization process operates very slowly or not at all, allowing eccentric orbits to persist. The orbital orientation matters as well. Binary orbits exist in three-dimensional space, and the orbital plane can be tilted at any angle relative to our line of sight from Earth. When we observe a binary, we're viewing a projection of the three-dimensional orbit onto the two-dimensional sky. The appearance depends on the orbital inclination, the angle between the orbital plane and the plane of the sky. An inclination of 0 degrees means the orbital plane is perpendicular to our line of sight, and we see the orbit face on. An inclination of 90 degrees means the orbital plane contains our line of sight, and we see the orbit edge on. For visual binaries, those we can resolve and see as separate stars through telescopes. The orbital inclination determines what we observe. A face-on orbit appears as the stars circling each other in the plane of the sky, maintaining constant separation as they move. An edge-on orbit shows the stars moving back and forth along a line, approaching and receding, but never separating much in the perpendicular direction. Intermediate inclinations produce elliptical apparent motions. From these observations, along with spectroscopic measurements of the stars' velocities, astronomers can determine the three-dimensional orbital geometry, the masses of the stars, and the physical scale of the system. Now let's explore how binary stars are classified. Astronomers divide binaries into several categories based on how they're detected and what observations reveal about them. Understanding these categories helps us appreciate the different techniques astronomers use and the different physical regimes binary systems can occupy. Visual binaries are the most straightforward category. These are binary systems where both stars can be resolved and seen separately through telescopes. The key requirement is sufficient angular separation. The two stars must be far enough apart on the sky that even through atmospheric blurring and the telescope's optical limitations, they appear as distinct points or disks of light. This typically means separations of at least 0.1 arcseconds with modern large telescopes, though the exact threshold depends on the telescope's aperture, the observing conditions, and the brightness difference between the stars. Visual binaries range from pairs separated by fractions of an arcsecond, requiring large professional telescopes to resolve, all the way up to extremely wide pairs separated by tens or even hundreds of arcseconds. easily split by small amateur telescopes or even binoculars. The famous pair Mizar and Alcor in the Big Dipper, visible as two distinct stars to the naked eye under dark skies, represents an extreme example of a wide visual binary, separated by about 12 arc minutes, roughly 1/3 the width of the full moon. For a visual binary, astronomers can directly measure the orbital motion over time. They take images at different epochs, precisely measuring the separation and position angle between the two stars. As decades or centuries pass, these measurements trace out the apparent orbit on the sky. With sufficient observations covering enough of the orbit, astronomers can fit an ellipse to the data and determine the orbital parameters, the period, the semi-major axis of the apparent orbit, the eccentricity, and the orientation. Combining these with a measurement of the system's distance from Earth converts the angular measurements into physical distances, allowing calculation of the true orbital size, and, through Kepler's third law, the total mass of the system. The challenge with visual binaries is time. Many have orbital periods of decades, centuries, or even millennia. The widest visual binaries may take hundreds of thousands of years to complete a single orbit. To determine accurate orbital parameters requires observations covering a substantial fraction of the orbit. For a binary with a 500-year period, astronomers need at least 50 to 100 years of measurements, and preferably more. The longest-running programs to study visual binaries span more than 2 centuries, with modern astronomers building on observations made by their predecessors in the 1700s and 1800s. This generational continuity exemplifies astronomy's role as one of the few sciences where data accumulates over timescales longer than individual human lifetimes. Spectroscopic binaries represent a completely different detection method. These systems are too close together for their stars to be resolved visually. Even through the largest telescopes, the binary appears as a single point of light, but spectroscopy reveals the truth. When astronomers spread the light into a spectrum, displaying the intensity, at each wavelength they see the characteristic absorption or emission lines that identify chemical elements in the star's atmospheres. For a spectroscopic binary, these spectral lines show periodic variations in their wavelengths due to the Doppler effect. As the stars orbit their barycenter, they alternately move toward and away from Earth along our line of sight. When a star moves toward us, its light is blue-shifted, compressed to shorter wavelengths. When it moves away, its light is red-shifted, stretched to longer wavelengths. The spectral lines shift back and forth, oscillating around their rest wavelengths with a period equal to the orbital period of the binary. By measuring these shifts, astronomers can determine the velocities of the stars along the line of sight, called radial velocities. If both stars are bright enough to show distinct spectral lines, astronomers see a double-lined spectroscopic binary. The spectrum shows 2 sets of lines, one from each star oscillating in opposite phase. When one star's lines are blue-shifted because it's moving toward us, the other star's lines are red-shifted because it's moving away. Half an orbital period later, the situation reverses. From these measurements, astronomers can determine the orbital period, the eccentricity if the orbit is elliptical, and the radial velocity amplitudes for both stars. The radial velocity amplitudes, combined with the orbital period, allow calculation of a quantity called the mass function, which depends on the stellar masses. and the orbital inclination. If the inclination is known or can be constrained, the individual stellar masses can be determined. Single-lined spectroscopic binaries show only one set of spectral lines. From the brighter star, the companion is too faint to contribute detectable spectral features. The visible star's lines still oscillate with the orbital period, revealing the binary nature even though we can't directly observe the companion. These systems are more challenging to analyze because we lack information about the companion's velocity. We can still measure the orbital period and the radial velocity amplitude of the visible star, but determining masses requires additional assumptions or observations. The inclination presents a fundamental ambiguity for spectroscopic binaries. Radial velocity measurements only capture the component of the orbital motion along our line of sight. If the orbit is inclined at an angle to the line of sight, the observed radial velocity is reduced by a factor of the sine of the inclination. This means we can't distinguish between a low inclination orbit with high intrinsic velocities and a high inclination orbit with lower intrinsic velocities if they produce the same observed radial velocity variations. This degeneracy affects mass determinations. The masses calculated from radial velocities alone are minimum masses, multiplied by an unknown factor that depends on the inclination. Only if additional information constrains the inclination can true masses be obtained. Eclipsing binaries solve the inclination problem. These are binary systems oriented nearly edge-on to our line of sight, so the orbital plane contains our viewing direction. As the stars orbit, they periodically pass in front of each other as seen from Earth, creating eclipses. The system's brightness drops when one star blocks light from the other. These brightness variations, plotted over time, create a light curve with periodic dips marking the eclipses. There are typically two minima in the light curve per orbital period. The primary minimum occurs when the fainter or cooler star passes in front of the brighter or hotter star, blocking the most luminous part of the system. The secondary minimum occurs half an orbit later, when the brighter star passes in front of the fainter star, blocking less light and creating a shallower dip. The shapes, depths, and durations of these eclipses depend on the sizes of the stars, their temperatures, the orbital inclination, and the eccentricity of the orbit. Detailed modeling of the light curve can extract all these parameters with remarkable precision. For an eclipsing binary, we know the inclination must be close to 90 degrees. This removes the inclination ambiguity from spectroscopic measurements. If we can obtain both light curves and radial velocity measurements for an eclipsing binary, we can determine nearly complete solutions for the system. The orbital period comes from either the light curve or the radial velocities. The radial velocities give the mass function, and the known inclination allows calculation of the actual masses. The light curve provides the stellar radii in units of the orbital separation. Combining all these measurements yields the individual masses, radii, and luminosities of both stars. These are the most precisely characterized binary stars, providing critical tests of stellar evolutions, theory, and calibrations for stellar parameters. Eclipsing binaries come in several varieties based on the shapes of their light curves. Algol type, or EA eclipsing binaries, show light curves that are flat between eclipses, with well-defined eclipse beginnings and ends. The flat portions indicate the stars are not strongly interacting and maintain nearly spherical shapes. Beta Lyrae, or EB eclipsing binaries, show continuously varying light curves with smooth, gradual eclipses. The continuous variation results from ellipsoidal distortion of one or both stars due to strong tidal forces and possibly mass transfer. W Ursae Majoris, or EW eclipsing binaries, show nearly equal primary and secondary minima and continuous variations between them. These are contact binaries where the stars are so close they touch, sharing a common envelope of gas. Astrometric binaries represent the fourth major detection category. In these systems, one star is bright enough to observe while the companion is too faint to detect directly. But the unseen companion's gravity affects the visible star's motion through space. As the binary orbits, the visible star wobbles back and forth around the system's barycenter. Precise measurements of the star's position over years reveal this wobble, proving the existence of the unseen companion. The amplitude of the wobble depends on the mass ratio of the two stars and the size of the orbit. A massive unseen companion produces a larger wobble than a low-mass one. A wide orbit produces a larger amplitude than a tight orbit, all else being equal. By measuring the wobble's amplitude and period, astronomers can constrain the companion's mass and orbital properties, though the orbital inclination introduces ambiguities similar to those for spectroscopic binaries. Astrometric detection requires extraordinarily precise position measurements. The wobbles are tiny, often measured in milliarcseconds or even microarcseconds. From the ground, Earth's atmospheric turbulence limits astrometric precision. Space-based observations avoid this limitation. The Hipparcos satellite in the 1990s measured positions of over 100,000 stars with milliarcsecond precision, discovering numerous astrometric binaries. The Gaia spacecraft, launched in 2013 and still operating, is measuring positions with microarcsecond precision for over 1 billion stars, revealing countless binaries and providing unprecedented orbital solutions for thousands of systems. The astrometric method became crucial for detecting exoplanets, planets orbiting other stars. A planet tugs on its host star just like an unseen binary companion, causing the star to wobble. The wobble from a planet is extremely small because planets have much less mass than stars, but ultra-precise astrometry can detect it. The first confirmed exoplanet around a sun-like star was discovered in 1995 using radial velocity measurements, but astrometric detections have confirmed and characterized many planets since then. Beyond these four main categories, there are hybrid classifications. Spectroscopic eclipsing binaries are eclipsing systems where we can also measure radial velocities, providing the most complete information possible. Visual spectroscopic binaries are systems wide enough to resolve visually, but also showing spectroscopic evidence of binary motion. Some systems have been studied using multiple techniques, each adding layers of information and improving our understanding. Now let's explore how binary stars form. This is a fundamental question with profound implications. Why do most stars form in pairs or multiples rather than alone? What processes in star-forming regions favor binary creation? The answers lie in the physics of gravitational collapse and the dynamics of protostellar disks. Stars form in molecular clouds, vast accumulations of gas and dust in the interstellar medium. These clouds are cold, with temperatures around 10 to 20 degrees above absolute zero. They're dense by interstellar standards, containing hundreds or thousands of hydrogen molecules per cubic centimeter. Despite this density, molecular clouds are still incredibly tenuous by everyday standards, far more rarefied than the best laboratory vacuums on Earth. But their enormous sizes, often spanning tens or hundreds of light years, mean they contain enough mass to form thousands or even millions of stars. Within a molecular cloud, gravity works to pull material together. Denser regions have stronger gravity and attract more material, becoming denser still. This runaway process is called gravitational collapse. But several factors resist collapse. The gas has pressure, thermal and turbulent motions that push outward against gravity. The cloud has magnetic fields threading through it, providing magnetic pressure support. And the cloud as a whole may be rotating, with angular momentum that must be conserved as material falls inward. For star formation to proceed, gravity must overcome these resistances. This happens when a region becomes dense and massive enough that its self-gravity exceeds the support from pressure, magnetic fields, and rotation. Such regions are called Jeans unstable, named after the physicist James Jeans, who first analyzed gravitational instability in the early 1900s. Once a region goes unstable, collapse accelerates. Gas falls inward, piling up at the center. As material accumulates, the temperature and density at the core rise. Eventually, when the core temperature reaches about 10 million degrees, hydrogen fusion ignites. A star is born. But here's the key question: why does this process so often produce pairs or multiple stars rather than single stars? Several mechanisms can lead to binary or multiple star formation. They're not mutually exclusive, and different mechanisms may dominate in different environments or for different stellar masses. One major mechanism is turbulent fragmentation of the collapsing cloud. Molecular clouds are turbulent, filled with chaotic motions at all scales. As a cloud region begins to collapse, turbulence can create fluctuations in density. If these fluctuations are large enough, multiple density peaks form within the collapsing region. Each peak becomes a separate center of collapse, forming its own protostar. The result is a multiple star system with two or more protostars embedded in the same collapsing cloud core. These protostars are gravitationally bound to each other from the beginning. As they accrete mass from the surrounding material, they also orbit each other, their mutual gravity shaping the infall of additional gas and dust. Observations of young stellar objects support turbulent fragmentation as an important binary formation mechanism. Radio and infrared observations that peer through the dust enshrouding forming stars reveal numerous examples of binary and multiple protostars within single cloud cores. These protostars are often widely separated initially, tens or hundreds of astronomical units apart. As they evolve and accrete material, their orbits can shrink or expand depending on how mass and angular momentum are distributed in the system. Interestingly, computer simulations suggest that turbulent fragmentation preferentially creates wide binaries. The initial separations when protostars form are typically quite large. Closer binaries with separations of just a few to tens of astronomical units are harder to explain through turbulent fragmentation alone. This has led astronomers to explore other mechanisms that can form tight binary systems. Disk fragmentation provides an alternative pathway. When a protostar forms, the cloud material falling onto it doesn't hit directly. conservation of angular momentum causes the infalling gas to form a rotating disk around the young star. This protoplanetary disk is the birthplace of planets in single-star systems, but under certain conditions, the disk itself can become gravitationally unstable and fragment into multiple clumps. If a clump is massive enough, it can collapse and form a second star within the disk, creating a binary system. Disk fragmentation requires specific conditions. The disk must be massive, containing a substantial fraction of the system's total mass. It must also be cool enough that thermal pressure doesn't prevent collapse of the fragments. And it must have low enough viscosity that gravitational instabilities can grow faster than they're smoothed out by the disk's internal motions. These conditions can be met in the massive disks around young, accreting protostars, especially early in the star formation process, when disks are most massive. The products of disk fragmentation tend to be closer binaries than those from turbulent fragmentation. Simulations show that disk fragmentation typically produces companions at separations of tens to a few hundred astronomical units. The newly formed secondary star orbits within the disk, possibly accreting additional material from the disk as it grows. The interactions between the stars and the disk can cause the orbit to evolve significantly during this early phase. There's intriguing observational evidence supporting disk fragmentation. Studies of young binary stars in star-forming regions have found that close binaries, those with separations less than about 200 astronomical units, often align with the rotation of their parent molecular cloud core. This alignment makes sense if the binaries formed from fragmentation of a disk that was rotating in sync with the core. Wider binaries show more random orientations, consistent with formation via turbulent fragmentation, where the connection to the large-scale rotation is weaker. A third possibility is dynamical capture. In dense stellar environments like young star clusters, stars can come close enough to capture each other gravitationally. However, the physics of gravitational capture is tricky. If two stars approach each other in isolation, their trajectories are determined by conservation of energy and angular momentum. They'll swing past each other in a hyperbolic orbit and separate again, exactly as they came together. For capture to occur, something must remove energy from the encounter. This could happen through interaction with a third star in a triple encounter, or through dissipation in a massive circumstellar disk that acts as a brake on the relative motion. Capture is probably not the dominant binary formation mechanism overall. The stellar densities needed for frequent encounters are found only in the densest regions of star-forming clouds and in young clusters. Most stars form in lower density environments where encounters are rare, and the capture process is inefficient. Most encounters don't result in bound binary formation. Nevertheless, dynamical interactions in clusters can modify binaries that formed through fragmentation. Close encounters can break up wide binaries, tighten or widen the orbits of existing binaries, and occasionally create new binaries through exchange interactions where an incoming star swaps places with one member of an existing binary. The evidence suggests that most binary stars form during the initial fragmentation and collapse of molecular cloud cores, either through turbulent fragmentation creating multiple protostars or through disk fragmentation around a single protostar. These primordial binaries then evolve as they accrete material, interact with their natal disks and envelopes, and potentially undergo dynamical interactions with neighboring forming stars. The final orbital properties we observe in mature binaries reflect this complex history. One fascinating line of evidence comes from a 2017 study by Sarah Sadavoy and Stephen Stoller. They analyzed observations of young protostars in the Perseus molecular cloud, about 600 light-years from Earth. The Perseus cloud is a typical low-mass star-forming region, creating stars similar to our Sun rather than massive stars. Sadavoy and Stoller found that all the very youngest Class 0 protostars, those less than about 500,000 years old that are in wide binary systems, show a peculiar alignment. These wide binaries, separated by more than 500 astronomical units, align preferentially along the long axis of the elongated cloud cores in which they formed. Slightly older Class 1 protostars, those 500,000 to a few million years old, show closer binary separations, around 200 astronomical units on average, and no alignment with the cloud core. Sadavoy and Stoller proposed a model to explain these patterns. They suggested that all stars form initially as wide binaries through fragmentation of collapsing cloud cores. The binaries are born with the wide separations and alignments observed in Class 0 systems. Then over time, two things happen. Some wide binaries are disrupted by dynamical interactions with other forming stars or by the tidal field of the cloud, becoming single stars. Other wide binaries have their orbits shrink due to interactions with the gas and dust surrounding them, becoming closer binaries. The net result is that by the time stars reach a few million years old, many that were born in binaries have become single, while others have tightened into closer binary configurations. This model suggests that our Sun and other apparently single stars may once have had binary companions that were lost during the chaotic early phases of star formation. It's possible that the Sun had a sibling star separated from it during the first few million years of the solar system's existence, now wandering somewhere else in the galaxy. We have no way to identify this hypothetical solar twin if it exists. It would be indistinguishable from billions of other Sun-like stars born around the same time. But the idea that even single stars, like our Sun, may have been born in binaries underscores just how common binary formation is. The frequency of binary systems varies with stellar mass. For the most massive stars, those containing tens of solar masses, essentially all of them are in binary or multiple systems. The precise frequency is difficult to determine because massive stars are rare and their lifetimes are short, but surveys find binarity rates of 70 to 80% or higher. For Sun-like stars, stars with masses between about half and twice the Sun's mass, roughly 40 to 50% are in binary or multiple systems. For the lowest mass stars, red dwarfs with less than half the Sun's mass, the binary frequency drops to perhaps 20 to 30%. Brown dwarfs, objects too small to sustain stable hydrogen fusion, rarely have companions. This trend with mass likely reflects differences in the star formation process at different mass scales. Massive stars form in the most violent and turbulent regions of molecular clouds, where fragmentation is rampant and multiple cores often form close together. The disks around young massive stars are also more likely to be gravitationally unstable and fragment. At lower masses, the formation process is gentler, turbulence is less extreme, and disks are less prone to fragmentation, resulting in a lower binary frequency. Let's now delve into one of the most important processes in binary star evolution, mass transfer. This phenomenon occurs when one star in a binary fills a critical gravitational boundary, called its Roche lobe, and begins transferring material to its companion. Mass transfer can completely alter the evolution of both stars, creating exotic systems and phenomena that would never occur in single stars. To understand mass transfer, we must first understand Roche lobes. In a binary system, each star creates a gravitational potential well, a three-dimensional surface representing the gravitational energy at each point in space. The combined potential from both stars creates a complex landscape. In the rotating reference frame that rotates with the binary, there are 5 special points called Lagrange points, where the gravitational forces from both stars and the centrifugal force from rotation balance exactly. The most important of these is the L1 Lagrange point, located between the two stars. The Roche lobe is the region of space around each star within which material is gravitationally bound to that star. The boundary of the Roche lobe passes through the L1 point. Material inside a star's Roche lobe will orbit that star. Material outside both Roche lobes is not bound to either star and will escape the system. Material at the L1 point is equally attracted to both stars and can flow freely from one Roche lobe to the other. The size of a star's Roche lobe depends on the mass ratio of the binary and the orbital separation. The more massive a star is relative to its companion, the larger its Roche lobe. Wider binaries have larger Roche lobes for both stars. An approximate formula for the Roche lobe radius, derived by astronomer Bohdan Paczynski, gives the radius in terms of the orbital separation and the mass ratio. For a star with mass m1, a binary with total separation A and companion mass m2, the Roche lobe radius is approximately RL, AX 0.49, x m1, m1 plus m2, 1 tor 3, 0.6 x cmm1, mom1 plus m2, 1 mom 3, plus l1, mom 1, mom 2, 1 3. In a young binary where both stars are on the main sequence, their radii are typically much smaller than their Roche lobe radii. The stars orbit each other without touching or interacting beyond their mutual gravitational pull. Such a system is called a detached binary, but as stars evolve, they change. Stars that exhaust the hydrogen in their cores expand dramatically as they become red giants. A star that once fit comfortably inside its Roche lobe can swell to fill and then exceed the lobe boundary. When a star's surface reaches its Roche lobe, material at the stellar surface near the L1 point experiences equal attraction to both stars. Further expansion causes material to overflow through L1, flowing toward the companion star. This is Roche lobe overflow, the primary mechanism for mass transfer in close binary systems. The material flowing through L1 carries angular momentum. Conservation of angular momentum usually prevents the transferred material from falling directly onto the companion star. Instead, the gas stream orbits the companion, forming a disk called an accretion disk. The accretion disk is a flat, rotating structure where gas gradually spirals inward toward the star, losing angular momentum through viscous friction and turbulent processes within the disk. As gas in the accretion disk spirals inward, it heats up due to friction and compression. The inner regions of the disk closest to the star become extremely hot, often reaching tens of thousands or even millions of degrees. At these temperatures, the disk emits copious radiation, sometimes outshining the stars themselves. The rate of mass transfer depends on how much the donor star overfills its Roche lobe and on the structure of the donor's outer layers. If a star only slightly overfills its Roche lobe, the overflow is gentle and the mass transfer rate is low, perhaps only a millionth of a solar mass per year or less. If the star significantly overfills its lobe, the mass transfer rate can be much higher, reaching thousandths or even hundredths of a solar mass per year. Such rapid mass transfer can last for relatively short times, just thousands to millions of years, before the donor exhausts its transferable material or the system reaches a new equilibrium. Mass transfer profoundly affects both stars. The donor star loses mass, which changes its structure and evolution. Losing mass from the outer envelope can expose deeper layers that were previously buried. If the donor is an evolved star with a helium core and hydrogen-rich envelope, mass transfer can strip away the envelope, revealing the hot, dense core. The exposed core may become a white dwarf or continue evolving in unusual ways. Not possible for single stars. The accreting star, the one receiving material, gains mass. This added material alters the star's structure, increasing its mass and potentially rejuvenating it. If the accreting star is on the main sequence, the extra mass can increase its luminosity and effective temperature, making it appear younger and more massive than it actually is. This creates the Algol paradox, named after the famous eclipsing binary Algol, where the less massive star appears more evolved than the more massive star. The resolution of the paradox is mass transfer. The currently less massive star was originally more massive and evolved first, transferring mass to its companion and reversing the mass ratio. The stability of mass transfer depends on how the donor star and its Roche lobe respond to mass loss. If the donor shrinks faster than its Roche lobe, when it loses mass, the transfer is stable. The star will settle back inside its lobe after losing some mass, and the transfer will proceed gradually, over long timescales. But if the Roche lobe shrinks faster than the star, the transfer is unstable. The star will overfill its lobe more and more as mass loss continues, leading to runaway mass transfer that can engulf both stars in a common envelope. For stars with convective envelopes, like red giants or low-mass main sequence stars, Roche lobe overflow is generally stable as long as the mass ratio is not too extreme. The star adjusts its size to match the changing Roche lobe radius. But if the donor is much more massive than the accretor, the mass transfer can be dynamically unstable. In this case, the donor overfills its lobe so much that mass transfer proceeds on the dynamical timescale, the time it takes for gravitational forces to significantly change the star's structure. This timescale is very short, minutes to hours, resulting in explosive mass transfer that rapidly engulfs the companion. Common envelope evolution occurs when mass transfer is dynamically unstable. The donor star's envelope expands rapidly, enveloping both stars in a thick, shared atmosphere. Friction between the stellar cores and the envelope causes the cores to spiral inward toward each other. Angular momentum and orbital energy are transferred to the envelope, which can be partially or entirely expelled from the system. The final outcome depends on how much energy is deposited into the envelope and how efficiently it can be ejected. In some cases, the cores merge, forming a single star. In other cases, the cores survive as a very close binary with an orbital separation measured in just a few solar radii. Common envelope evolution is thought to be crucial for forming many types of compact binaries, systems containing white dwarfs, neutron stars, or black holes orbiting normal stars or other compact objects. The only way to bring compact objects close enough to interact significantly is through common envelope evolution that shrinks the orbit dramatically. Without this process, compact binaries would be much rarer than observed. Let's examine some specific examples of mass transfer systems. Algol itself, Beta Persei, is the prototype of semi-detached binaries where mass transfer has occurred or is ongoing. Algol is an eclipsing binary with a period of 2.87 days. The primary star is a hot, massive B-type main sequence star with about 3.6 solar masses. The secondary is a cooler, less massive G-type subgiant with about 0.8 solar masses. But here's the paradox. The less massive secondary is more evolved, having already exhausted its core hydrogen and begun expanding off the main sequence. The more massive primary should evolve faster, yet it appears younger. The resolution is that the secondary was originally the more massive star. It evolved first, filled its Roche lobe, and transferred most of its mass to what is now the primary. The mass transfer reversed the mass ratio, creating the seemingly contradictory situation we observe today. The secondary in Algol currently fills its Roche lobe, appearing teardrop-shaped rather than spherical. The L1 point is visible as an elongated extension of the star pointing toward the primary. Material flowing through L1 forms an accretion disk around the primary, though the mass transfer rate is now quite low. The system has reached a quasi-equilibrium state, where the secondary's evolution drives slow ongoing mass transfer, but the rate is low enough to be stable over long time scales. Beta Lyrae represents a more extreme case. In this system, mass transfer is so vigorous that the entire system is surrounded by a thick disk of gas. The two stars orbit with a period of only 12.9 days. The primary is a massive B-type star, while the secondary is even more massive, but hidden within the surrounding gas. The system's light curve shows continuous variation throughout the orbit, never reaching a constant brightness between eclipses. This continuous variation comes from the ellipsoidal distortion of the stars and the emission from the extensive gaseous envelope surrounding them. Beta Lyrae systems represent a phase of rapid mass transfer, possibly approaching or in common envelope evolution. They're transitioning rapidly on astronomical timescales, making them rare but fascinating objects to study. Ursae Majoris systems take close interaction to the extreme. These are contact binaries, where both stars fill their Roche lobes simultaneously. The two stars actually touch, sharing a common envelope of gas. The stars are so close that they orbit in just hours, with orbital periods typically ranging from a few hours to half a day. Despite their close proximity, the stars don't merge because they are rotating synchronously with the orbit, presenting the same face to each other at all times. The shared envelope mixes material between the two stars, creating an unusual configuration where both stars have similar surface temperatures despite potentially different masses. The light curves of W, Ursae Majoris binaries, show nearly equal primary and secondary eclipses, reflecting the similar temperatures and sizes of the two components. Contact binaries are thought to be the end point of orbital evolution for some close binaries. As angular momentum is lost from the system through magnetic braking or gravitational radiation, the orbit shrinks. The stars move closer together. Their Roche lobes shrink, and eventually both stars fill their lobes simultaneously. Once in contact, the system can remain stable for long periods. However, the ultimate fate of contact binaries is uncertain. Some may merge to form single, rapidly rotating stars. Others may be disrupted by dynamical instabilities. Observations of contact binaries in different states of evolution are helping to constrain their life cycles. Mass transfer doesn't just affect the stars, it also affects the orbit itself. When mass is transferred from one star to another, angular momentum is redistributed. If the mass is transferred conservatively, meaning all the transferred mass is retained by the accretor, the orbit responds according to well-established formulas. For a circular orbit, if mass is transferred from the more massive to the less massive star, the orbit expands. If mass is transferred from the less massive to the more massive star, the orbit shrinks. These changes reflect conservation of angular momentum in the system, but mass transfer is often non-conservative. Some material may be lost from the system entirely, carrying away angular momentum. Material can escape through the outer Lagrange points, L2 and L3, if it gains enough energy. It can also be expelled in winds from the accretion disk or from the accreting star if the mass transfer rate exceeds what the star can accommodate. The way mass and angular momentum are lost from the system critically affects the orbital evolution and the ultimate fate of the binary. Now let's explore some of the most exotic binary systems, those containing compact objects like white dwarfs, neutron stars, and black holes. These systems showcase extreme physics, generating phenomena visible across vast distances and providing unique laboratories for testing fundamental theories. White dwarf binaries are systems where one or both stars have evolved off the main sequence and shed their outer envelopes, leaving behind dense white dwarf cores. White dwarfs are incredibly compact, packing a mass comparable to the Sun into a volume the size of Earth. Their densities are about 1,000,000 times greater than water. The matter in a white dwarf is supported against gravity by electron degeneracy pressure, a quantum mechanical effect arising from the Pauli exclusion principle that forbids electrons from occupying the same quantum state. When a white dwarf is in a close binary with a normal star, mass transfer can create dramatic effects. As the normal star evolves and fills its Roche lobe, material streams onto the white dwarf. Because the white dwarf is so small and dense, the accreting material forms a thin, hot accretion disk. Material in the inner disk reaches temperatures of tens of thousands of degrees, emitting strongly in ultraviolet and X-rays. As material gradually spirals inward and accumulates on the white dwarf's surface, a layer of hydrogen-rich gas builds up. Under the right conditions, this accumulated hydrogen can ignite explosively. The white dwarf's surface is extremely hot and dense. When the hydrogen layer builds up to a critical mass, the temperature and pressure at its base become high enough to trigger runaway thermonuclear fusion. The hydrogen layer detonates in a flash that releases tremendous energy, brightening the system by factors of tens of thousands or millions. This is a classical nova, a stellar explosion that can briefly make the binary visible to the naked eye even from great distances. Classical novae are not one-time events. After a nova eruption blows off the accumulated hydrogen, the white dwarf and its companion continue orbiting. Mass transfer resumes, building up a new hydrogen layer. Eventually, another nova erupts. This cycle can repeat multiple times over millions of years. Some novae have been observed to recur on timescales of just decades, earning them the designation recurrent novae. If the white dwarf is close to the Chandrasekhar limit, the maximum mass a white dwarf can support, around 1.4 solar masses, continued mass accretion can push it over this limit. When a white dwarf exceeds the Chandrasekhar mass, electron degeneracy pressure can no longer support it against gravity. The entire star collapses in a fraction of a second, triggering explosive carbon fusion throughout the white dwarf. The star is completely destroyed in what's called a Type Ia supernova. Type Ia supernova are among the most energetic explosions in the universe. They release as much energy as the Sun will emit over its entire 10 billion year lifetime, all in a few weeks. The peak brightness is remarkably consistent from one Type Ia supernova to another because they all result from white dwarfs near the same mass limit exploding in the same way. This consistency makes Type Ia supernovae excellent standard candles for measuring cosmic distances. By comparing the observed brightness of a Type Ia supernova to its known intrinsic brightness, astronomers can calculate the distance to the host galaxy. This technique has been crucial for mapping the expansion history of the universe and for the discovery that the universe's expansion is accelerating, a finding recognized with the 2011 Nobel Prize in Physics. Neutron star binaries elevate the extremity even further. Neutron stars form when massive stars, those born with more than about 8 solar masses, exhaust their nuclear fuel and collapse. The iron core of such a star collapses in a fraction of a second, compressing to densities where protons and electrons merge into neutrons. The core becomes a neutron star, an object about 20 kilometers across with a mass of 1.4 to 2.5 solar masses. The density is comparable to the atomic nucleus, roughly 100 trillion times denser than water. A teaspoon of neutron star material would weigh about 1 billion tons on Earth. When a neutron star is in a binary with a normal star, mass transfer creates an X-ray binary. Material flowing from the normal star toward the neutron star releases gravitational potential energy. As the gas spirals inward through the accretion disk, it heats to tens of millions of degrees. At these temperatures, the disk emits primarily in X-rays. The neutron star's strong magnetic field can channel the accreting material toward its magnetic poles, creating hotspots that emit X-rays in beams. As the neutron star rotates, these beams sweep across space like a lighthouse. If Earth lies in the path of a beam, we detect pulses of X-rays. These systems are called X-ray pulsars. The X-ray luminosities of accreting neutron stars can be enormous. They commonly emit 1 trillion times the sun's luminosity in X-rays, making them visible across millions of light years. The brightest X-ray binaries can be detected in distant galaxies, providing valuable information about stellar populations and evolution in those galaxies. Some neutron star binaries contain 2 neutron stars orbiting each other. These binary neutron star systems form when both stars in an originally massive binary undergo supernova explosions. The first star to explode leaves a neutron star behind. Later, when the companion star explodes, it too leaves a neutron star, and the system becomes a binary neutron star pair. These systems are rare because both stars must be massive enough to form neutron stars, and the binary must remain bound through both supernova explosions, which can impart significant velocity kicks to the neutron stars. The first binary neutron star system was discovered in 1974 by Russell Hulse and Joseph Taylor. They found a pulsar, a rapidly rotating neutron star emitting radio pulses that showed periodic variations in its pulse arrival times. These variations indicated the pulsar was orbiting an unseen companion, which turned out to be another neutron star. The system, designated PSR B1913+16, has an orbital period of about 7.75 hours. Over the years since its discovery, Hulse and Taylor carefully timed the pulsar's pulses and found that the orbital period was decreasing. The two neutron stars were spiraling closer together at exactly the rate predicted by general relativity for gravitational wave emission. This provided the first indirect evidence for gravitational waves, confirming a key prediction of Einstein's theory. Hulse and Taylor received the 1993 Nobel Prize in Physics for this discovery. Binary neutron star systems eventually merge as gravitational wave emission shrinks their orbits. The inspiral accelerates as the neutron stars approach each other. In the final seconds, the stars orbit hundreds of times per second, emitting gravitational waves at kilohertz frequencies. When they finally touch, the merger is catastrophic. The collision creates an extraordinarily dense, hot remnant that may briefly be a hypermassive neutron star or may collapse immediately into a black hole. The merger ejects material rich in neutrons, which undergo rapid neutron capture nuclear reactions to build up heavy elements. This R-process nucleosynthesis is thought to be a major source of gold, platinum, and other heavy elements in the universe. The first detected gravitational waves from a binary neutron star merger came on August 17, 2017. The LIGO and Virgo gravitational wave detectors observed the signal, designated GW172817, from a binary neutron star merger in the galaxy NGC 4993, about 140 million light-years away. The gravitational wave signal lasted about 100 seconds as the neutron stars spiraled together. About 1.7 seconds after the gravitational wave signal ended, NASA's Fermi satellite detected a short gamma-ray burst from the same direction. Over the following hours and days, telescopes across the electromagnetic spectrum observed the merger's afterglow, from radio waves through optical light to X-rays and gamma rays. This multi-messenger observation, combining gravitational waves with electromagnetic radiation, opened a new era in astronomy. It provided direct confirmation that binary neutron star mergers produce short gamma-ray bursts and heavy elements, and it allowed precise tests of general relativity and measurements of the expansion rate of the universe. Black hole binaries represent the most extreme binary systems, when the most massive stars exhaust their fuel and collapse. The core is too massive to form a stable neutron star. Instead, it collapses completely, forming a black hole. Black holes are regions of space-time where gravity is so strong that not even light can escape. The boundary of a black hole is the event horizon, a one-way surface where the escape velocity equals the speed of light. Anything crossing the event horizon is forever lost to the outside universe, unable to send signals or escape. Stellar mass black holes, those formed from collapsing stars, typically have masses between about 5 and 20 solar masses, though the range may extend higher. When a black hole is in a binary with a normal star, mass transfer can occur just as with white dwarfs or neutron stars, but the accretion process is even more violent. Material spiraling toward a black hole reaches velocities close to the speed of light. The inner accretion disk, just outside the event horizon, becomes incredibly hot, reaching temperatures of millions or even hundreds of millions of degrees. The disk emits copious X-rays and gamma rays, making black hole binaries some of the brightest X-ray sources in the sky. The classic black hole binary is Cygnus X1, discovered in 1964 as a powerful X-ray source in the constellation Cygnus. Optical observations showed it was associated with a blue supergiant star. The star's spectrum showed periodic Doppler shifts, revealing it was in a binary with an unseen companion. The orbital period was 5.6 days. By measuring the star's radial velocity variations and estimating its mass, astronomers could calculate the mass of the unseen companion. The result was startling. The companion had a mass of at least 7 solar masses, but was completely dark at all wavelengths. No known object, except a black hole, could be so massive yet invisible. Cygnus X1 became one of the first widely accepted black hole candidates, though definitive proof remained elusive for years because black holes can't be directly observed. Modern observations using improved techniques have refined our understanding of Cygnus X1. The black hole's mass is now estimated at about 21 solar masses, significantly higher than early estimates. The distance to the system is about 7,200 light-years. The X-ray luminosity varies on timescales from milliseconds to months, reflecting complex dynamics in the accretion disk and near the event horizon. The system provides a unique laboratory for studying matter in extreme gravitational fields and for testing general relativity in the strong field regime near a black hole. Binary black holes, systems with 2 black holes orbiting each other, are among the most extreme objects in the cosmos. They form when both stars in a massive binary undergo core collapse, leaving 2 black holes behind. The system must survive both supernova explosions, which can disrupt the binary if too much mass is lost, or if the explosions impart large velocity kicks. But if the binary remains bound, the 2 black holes will orbit each other, gradually spiraling inward due to gravitational wave emission. The first direct detection of gravitational waves came from a binary black hole merger. On September 14, 2015, the 2 LIGO detectors in the United States simultaneously observed a gravitational wave signal designated GWAM-414. The signal was the characteristic chirp of a binary inspiral and merger, a rising tone as the orbit shrank and the gravitational wave frequency increased, culminating in a peak and then a ring down as the merged black hole settled into equilibrium. Analysis showed the signal came from 2 black holes with masses of about 36 and 29 solar masses, merging at a distance of about 1.3 billion light-years. The merger produced a final black hole of about 62 solar masses. The missing 3 solar masses of mass energy was radiated away as gravitational waves in a fraction of a second. At the peak of the merger, the gravitational wave luminosity exceeded the combined electromagnetic luminosity of all stars in the observable universe. This detection, announced in February 2016, was a watershed moment for physics and astronomy. It confirmed the existence of gravitational waves, a prediction of general relativity made by Einstein a century earlier. It proved that binary black holes exist and merge within the current age of the universe, and it inaugurated gravitational wave astronomy as a new field, opening a completely different window on the cosmos. Since that first detection, LIGO and its European counterpart Virgo have detected dozens of binary black hole mergers, along with binary neutron star mergers, and neutron star black hole mergers. Each detection provides information about the masses, spins, and orbital properties of the merging objects. The distribution of black hole masses has revealed that stellar mass black holes are more massive than previously thought, with some mergers involving black holes of 50, 60, or even over 80 solar masses. These high masses challenge our understanding of stellar evolution and supernova physics, as stars at massive were expected to collapse completely without leaving remnants. The detections also provide tests of general relativity, confirming its predictions with exquisite precision, even in the most extreme gravitational environments. Let's turn our attention to some of the most famous binary star systems, the ones that have taught us the most about stellar physics and captured the imagination of astronomers across the centuries. Sirius, the brightest star in Earth's night sky, is actually a binary system. The primary, Sirius A, is a brilliant white main sequence star with about 2 solar masses and 25 times the Sun's luminosity. It sits just 8.6 light-years from Earth, making it one of our closest stellar neighbors. The secondary, Sirius B, is a white dwarf, the first white dwarf ever discovered. The discovery of Sirius B is a tale of mathematical prediction and careful observation. In 1844, the German astronomer Friedrich Bessel noticed that Sirius was not moving through space in a straight line. Its proper motion, the apparent motion across the sky due to the star's actual motion through the galaxy, showed a slight wobble. Bessel realized this wobble indicated an unseen companion pulling gravitationally on Sirius. He predicted the companion would be discovered when telescopes became powerful enough to resolve it near the overwhelming glare of Sirius A. In 1862, the American telescope maker and astronomer Alvin Graham Clark tested a new 18.5-inch refracting telescope by observing Sirius. He noticed a faint star very close to Sirius that no one had reported before. This was Sirius B, confirmed as the companion Bessel had predicted. The orbital period was later determined to be about 50 years, with the 2 stars separated by an average of about 20 astronomical units, roughly the distance from the Sun to Uranus. The puzzle was Sirius B's nature. It was extremely faint, about 10,000 times dimmer than Sirius A, yet it had a measurable mass from its gravitational effect on Sirius A, about 1 solar mass. To be so faint yet so massive, it had to be incredibly dense and small. Early estimates suggested it was about the size of Earth. Spectroscopic observations in the 1910s showed Sirius B had a very hot surface temperature, over 25,000 degrees, hotter than Sirius A. A hot surface should produce high luminosity according to the Stefan Boltzmann law. The only way to reconcile the high temperature with the low luminosity was a tiny surface area. Sirius B was indeed Earth-sized. This raised a profound puzzle. How could a star be so dense? The answer came from quantum mechanics. In 1926, the physicist Ralph Fowler showed that matter in white dwarfs is supported by electron degeneracy pressure, a quantum effect that becomes important at extreme densities. Sirius B was a white dwarf, a stellar remnant where electron degeneracy prevents further collapse. This discovery opened the door to understanding stellar death and the ultimate fates awaiting stars like our Sun. Mizar and Alcor, as we discussed earlier, form one of the most famous visual doubles, easily visible to the naked eye, in the handle of the Big Dipper. But the Mizar-Alcor system is far more complex than it initially appears. Mizar itself was the first double star discovered telescopically in 1617. Then in 1889, Mizar A was revealed as a spectroscopic binary, the first ever found. Later observations showed Mizar B is also a spectroscopic binary, making Mizar a quadruple system. And in 2009, Alcor was discovered to be a binary as well, adding 2 more stars to the system. The Mizar-Alcor system contains at least 6 stars, all gravitationally bound and moving through space together as members of the Ursa Major moving group, a loose association of stars that formed together and are gradually dispersing as they orbit the galaxy. Algol Beta Persei earned the nickname the Demon Star from ancient observers who noticed its brightness variations. Every 287 days, Algol dims noticeably for about 10 hours before returning to normal brightness. This regular variation puzzled observers for centuries. In 1782, the young English astronomer Johannes Goodricke proposed a radical explanation. Algol's brightness variations were caused by a dark companion star passing in front of the bright primary star, creating eclipses. Goodricke's interpretation was correct. Algol was the first eclipsing binary identified, opening up a new method for studying stellar properties. Modern observations show Algol is actually a triple star system. The primary eclipsing binary consists of a 3.6 solar mass B-type main sequence star and a 0.8 solar mass G-type subgiant. A third star, a less massive main sequence star, orbits the eclipsing pair with a period of about 1.86 years. The most interesting aspect of Algol is the mass transfer that occurred in its past. The current subgiant was originally more massive than the current primary. It evolved first, transferred most of its mass to the primary, and reversed the mass ratio. This scenario, now called Algol-type evolution, is thought to be common in close binaries. Cygnus X1 holds a special place in astrophysics as one of the first black hole candidates and one of the brightest X-ray sources in the sky. Discovered by an X-ray telescope aboard a rocket flight in 1964, Cygnus X1 was identified with a blue supergiant star about 7,200 light-years away. The star's spectrum showed it was orbiting an unseen companion every 5.6 days. The companion's mass, calculated from the orbital dynamics, exceeds 7 solar masses and is likely around 21 solar masses based on modern measurements. No known object, except a black hole, can be that massive, yet completely dark. The X-rays come from an accretion disk around the black hole, heated to millions of degrees by the gravitational energy released as material spirals inward. Cygnus X1 has been continuously observed for over 50 years, providing insights into black hole, accretion physics, and the behavior of matter in strong gravitational fields. PSR B1913+16, the Hulse-Taylor binary pulsar discovered in 1974, provided the first evidence for gravitational waves and the first precise confirmation of general relativity's predictions for strong field gravity. The system contains 2 neutron stars in a tight orbit, with a period of 7.75 hours. One neutron star is a pulsar, emitting radio pulses 17 times per second. By timing the arrival of these pulses with exquisite precision, Hulse and Taylor measured the orbital parameters to extraordinary accuracy. They found the orbit was shrinking at exactly the rate predicted by general relativity for energy loss through gravitational wave emission. Over the decades since the discovery, the orbital decay has continued exactly as predicted, now accumulating to a shift of over a minute in the orbital period. The 2 neutron stars will merge in about 300 million years, an event that will produce gravitational waves detectable by instruments like LIGO and Virgo. These famous systems are just highlights from a catalog of tens of thousands of known binary stars. Each system is unique, with its own combination of stellar types, orbital parameters, and evolutionary state, yet they all follow the same physical laws and tell variations on common themes: gravitational interaction, orbital evolution, mass transfer, and the interplay between stellar evolution and binary dynamics. Now let's explore a topic that bridges binary stars and planetary science: circumbinary planets. These are planets that orbit both stars in a binary system, rather than orbiting just one star, while the other star is distant. The most famous fictional circumbinary planet is Tatooine, Luke Skywalker's homeworld in Star Wars, where twin suns set together over the desert landscape. For decades, Tatooine seemed like pure fantasy. How could a planet maintain a stable orbit around two stars? Wouldn't the gravitational perturbations tear the planet apart or fling it out of the system? The answer, surprisingly, is that circumbinary orbits can be quite stable under the right conditions. If a planet orbits both stars at a distance large enough compared to the binary separation, the two stars act almost like a single-point mass. The planet's orbit can be long-lived and stable. Computer simulations showed this was possible before any circumbinary planets were actually discovered. But finding such planets observationally was challenging. The breakthrough came from NASA's Kepler Space Telescope, launched in 2009 to search for exoplanets using the transit method. This technique looks for tiny dips in a star's brightness caused by a planet passing in front of it. For a circumbinary system, the geometry is more complex. The planet can transit either star or both stars, and the timing of transits is not perfectly periodic because the planet's orbit around the binary and the binary's orbit around their barycenter combine in complex ways. But Kepler's exquisite photometric precision could detect these subtle patterns. In 2011, astronomers announced the discovery of Kepler-16b, the first confirmed circumbinary planet. The system consists of two stars orbiting each other every 41 days. One star is a K-type orange dwarf with about 69% of the Sun's mass. The other is a much smaller red dwarf with only 20% of the Sun's mass. The planet, with a mass similar to Saturn, orbits both stars with a period of 229 days at a distance of about 0.7 astronomical units. The planet's transits across both stars created a complex but unmistakable pattern in Kepler's data. Kepler-16b is a gas giant, not a rocky world, so it's not a perfect analog to Tatooine. Its surface temperature is too cold for liquid water, well outside the habitable zone. But the discovery proved that circumbinary planets exist and can maintain stable orbits. It opened the door to finding more such planets and to considering whether Earth-like worlds could orbit binary stars. Since Kepler-16b, about a dozen circumbinary planets have been confirmed. Most are gas giants, similar in size to Neptune or Saturn. This observational bias likely reflects the detection method. Larger planets produce deeper transits and are easier to find. Smaller, rocky circumbinary planets almost certainly exist, but are harder to detect with current instruments. The Transiting Exoplanet Survey Satellite, TESS, which succeeded Kepler, has found additional circumbinary planets, and future missions will continue expanding the catalog. The formation of circumbinary planets is thought to follow the same basic process as planet formation around single stars. A protoplanetary disk forms around the young binary. Dust grains in the disk collide and stick together, gradually building up larger bodies. These planetesimals continue growing through collisions, eventually forming protoplanets. The gravitational influence of the binary creates gaps and structure in the disk, potentially affecting where and how planets form. Computer simulations suggest that circumbinary planets likely form farther from the binary than their current observed locations, then migrate inward through interactions with the disk gas. The habitability of circumbinary planets is a topic of active research. The presence of two stars complicates the habitable zone, the region where liquid water can exist on a planetary surface. The total stellar luminosity varies as the stars orbit each other, being brightest when both stars are on the same side of the planet and dimmest when they're on opposite sides. This creates periodic variations in the amount of sunlight the planet receives. For some orbital configurations, these variations could be extreme enough to destabilize the climate, causing the planet to freeze and thaw with each cycle. But for other configurations, particularly when the binary is tight and the planet orbits at a sufficient distance, the variations are modest and a stable climate is possible. One intriguing system is Kepler-47, which contains 3 circumbinary planets. The binary consists of a sun-like star and a red dwarf orbiting each other every 745 days. 3 planets orbit the binary at distances ranging from 0.3 to 0.99 astronomical units. The outermost planet, Kepler-47d, orbits within the habitable zone. It's a gas giant, so not habitable itself, but if it has large moons, those moons might be warm enough for liquid water. This raises the tantalizing possibility of habitable moons orbiting circumbinary gas giants, combining the Tatooine scenario with the Avatar scenario of life on an exomoon. Binary stars may even enhance habitability in some circumstances. A 2024 study by Milena Rice and colleagues found that many binary systems have aligned configurations where the stellar rotation axis and the orbital axis of the binary all point in similar directions. This alignment suggests the systems formed from orderly rotating disks rather than chaotic fragmentation. For circumbinary planets, this alignment means more stable, predictable variations in stellar radiation. The study also noted that binary companions can help tame the wild behavior of young stars, particularly red dwarfs, which are prone to powerful flares, and stellar winds that can strip planetary atmospheres. A binary companion's tidal forces can slow down stellar rotation, reducing flare activity and creating a gentler environment for planetary atmospheres to survive. Research by Paul Mason and collaborators has explored this taming effect in detail. Young stars rotate rapidly and have strong magnetic fields that generate intense stellar winds and radiation. For single red dwarfs, this hyperactive phase can last billions of years, potentially sterilizing any planets in the habitable zone. But in a binary, tidal forces from the companion slow the star's rotation much more quickly. The stellar wind weakens, flare activity diminishes, and the environment becomes more hospitable. This suggests that planets in certain binary systems might actually be more habitable than planets around similar single stars. The picture emerging is that circumbinary planets are likely common, perhaps as common as planets around single stars. They can form through standard planet formation processes. They can maintain stable orbits and stable climates under a range of conditions, and they might even benefit from the binary environment in some ways The romantic image of a world with two suns, far from being impossible, may represent a common configuration throughout the galaxy. Let's examine what modern research is revealing about binary stars and what questions remain unanswered. The field of binary star research is vibrant and rapidly evolving, with new discoveries and insights emerging regularly. The Gaia spacecraft, launched by the European Space Agency in 2013, is revolutionizing our knowledge of binary stars. Gaia is measuring the positions, distances, and motions of over 1 billion stars with unprecedented precision. For binary stars, Gaia's observations reveal orbital motions in exquisite detail. Wide binaries that would take centuries to trace out a complete orbit can now have their orbital parameters determined from just a few years of Gaia data, thanks to the mission's micro-arcs, second-level astrometric precision. Gaia has discovered thousands of new binary systems and is providing the most accurate mass measurements ever obtained for countless binaries. One of Gaia's key contributions is revealing the three-dimensional structure of the galaxy and the stellar populations within it. This includes mapping binary populations in different environments: the galactic disk, the halo, star clusters, and star-forming regions. These maps show how binary properties vary with location, age, and metallicity. They're helping to constrain star formation theories and binary evolution models. The data pouring in from Gaia will keep astronomers busy for decades, extracting new insights from this unprecedented census of the galactic neighborhood. Gravitational wave astronomy is opening entirely new ways to study binary stars, particularly the most exotic ones containing compact objects. The LIGO and Virgo detectors, operating since 2015, have detected nearly 100 gravitational wave events as of 2024, mostly binary black hole mergers, but also including binary neutron star mergers and neutron star black hole mergers. Each detection provides information about the masses and spins of the merging objects, the properties of space-time in extreme gravitational fields, and the environments where these systems form and evolve. Future gravitational wave detectors will expand our reach. The Einstein telescope, planned for construction in Europe in the 2030s, will be about 10 times more sensitive than current detectors. It will detect binary mergers across the entire observable universe, seeing back to when the first stars and black holes formed. The Cosmic Explorer proposed for the United States will have similar capabilities. These next-generation detectors will observe thousands of binary mergers per year, providing unprecedented statistics on binary populations and enabling precision tests of general relativity. The Laser Interferometer Space Antenna, LISA, planned for launch in the 2030s, will detect gravitational waves from space, accessing lower frequencies than ground-based detectors can reach. LISA will observe merging massive black holes in distant galaxies, ultra-compact binaries in our own galaxy, and perhaps even the gravitational wave background from countless binaries throughout the universe. The combination of ground-based and space-based gravitational wave astronomy will give us a complete picture of the gravitational wave spectrum and the binary systems that populate it. Questions remain about many aspects of binary stars. The precise mechanisms by which most binaries form are still debated. How common is turbulent fragmentation versus disk fragmentation? How do primordial binary orbits evolve as protostars interact with their surroundings? What determines the final distribution of orbital periods and mass ratios we observe? Common envelope evolution, crucial for forming compact binaries, is poorly understood. The process is so rapid and three-dimensional that it's challenging to simulate accurately. We don't know exactly how efficiently orbital energy is transferred to the envelope and how much material can be ejected. Different assumptions about these efficiency factors lead to vastly different predictions for the numbers and properties of compact binaries. Improved simulations and observations of potential common envelope precursors are needed to resolve these uncertainties. The origins of the most massive stellar black holes detected by LIGO are puzzling. Stellar evolution theory suggests that very massive stars should lose most of their mass through stellar winds before collapsing, preventing formation of black holes much above 40 or 50 solar masses. Yet LIGO has detected black holes with 60, 70, or even over 80 solar masses. How did these monsters form? Possible explanations include hierarchical mergers, where black holes merge multiple times in dense stellar environments, building up mass through successive mergers. Or perhaps stellar physics in low metallicity environments, where stars have fewer heavy elements and thus weaker stellar winds, allows more massive black holes to form directly from stellar collapse. Resolving this question will require better understanding of both stellar evolution and the dynamics of dense stellar systems, where black holes might interact and merge repeatedly. The role of binary stars in the chemical evolution of galaxies is another active research area. Binary interactions, particularly mass transfer and mergers, can significantly alter stellar evolution and nucleosynthesis. Massive binaries evolve differently than single massive stars, potentially producing different patterns of element production. Type Ia supernovae from white dwarf. Binaries are major sources of iron and other iron group elements. Understanding the full impact of binaries on galactic chemical evolution requires detailed models that account for the complex interactions and the range of possible outcomes. Binary stars also factor into understanding stellar populations in distant galaxies. When we observe a galaxy, we see the integrated light from billions of stars. To interpret that light, we need population synthesis models that predict what stellar populations should look like, given certain star formation histories and metallicities. These models must account for binary stars because binaries are so common, and because their evolution differs from single stars. Models that ignore binaries or treat them simplistically will give incorrect predictions for galaxy properties. Improved binary population synthesis models are essential for extracting accurate information about distant galaxies from their integrated light. The ultimate fate of the Milky Way and Andromeda galaxies, which are approaching each other and will merge in about 4 billion years, involves countless binary star interactions. When galaxies merge, their stellar populations mix, and close encounters between stars become more common. Binary stars can be disrupted, with one star remaining, bound to the merged galaxy while the other is ejected at high velocity, becoming a hypervelocity star traveling through intergalactic space. Conversely, single stars can capture each other during close encounters, forming new binaries. The galaxy merger simulations that predict the outcome of the Milky Way Andromeda collision must account for these binary processes to accurately model the result. Let's explore in more detail the incredible variety of stellar types that can exist in binary systems and how their interactions create the diversity we observe. The range of possible binary combinations is vast, limited only by the types of stars that exist and the physics of their interactions. Consider a binary system containing two main sequence stars of similar mass and age. Both stars are fusing hydrogen in their cores, shining steadily as they convert mass into energy. They orbit their common barycenter, completing their orbits in periods ranging from hours to millions of years, depending on their separation. These are the simplest binaries, relatively calm and predictable. Their evolution proceeds much like single stars would evolve, with one crucial difference. When the first star begins to swell into a red giant, its companion is still right there, close enough to potentially interact. The more massive star in such a pair will evolve first because massive stars burn through their fuel faster than low-mass stars. When this star exhausts the hydrogen in its core, it begins expanding. Its outer layers cool and redden, and the star swells to enormous size. If the binary is close enough, this expansion brings the star's surface to its Roche lobe. Mass transfer begins. The less massive star, still on the main sequence, suddenly finds itself receiving a steady stream of material from its evolving companion. This material forms an accretion disk, spiraling inward and eventually adding to the star's mass. The accreting star becomes overluminous for its age. It now has more mass than it started with, which increases its core temperature and pressure, accelerating its fusion rate. The star shines more brightly than a single star of the same age would. Meanwhile, the donor star loses mass. Stripping away its outer envelope can halt, or even reverse its evolution. If enough mass is lost, the donor may never complete its red giant phase, instead being stripped down to its helium core and becoming a hot, compact helium star or subdwarf. This is just one evolutionary pathway among many. Now consider a binary where one star is significantly more massive than the other, perhaps a 15 solar mass star paired with a 5 solar mass companion. The massive star races through its evolution. It spends only about 10 million years on the main sequence, compared to billions of years for a sun-like star. The massive star swells into a supergiant, potentially filling its Roche lobe and transferring mass. Then, after exhausting its nuclear fuel, it explodes as a supernova. The explosion is violent, releasing energy equivalent to the sun's entire lifetime output in just a few seconds. The blast wave expands at thousands of kilometers per second, slamming into any nearby material. If the binary survives this explosion, it now contains the supernova remnant, either a neutron star or black hole, orbiting the normal companion star. The system has been transformed. The supernova may have imparted a velocity kick to the remnant, changing the orbital parameters. Some fraction of the binary's mass was lost in the explosion, which affect the orbit according to conservation of angular momentum. If too much mass was lost, the binary may be disrupted entirely, the two components flying apart and becoming separate single objects. But if the binary survives, it enters a new phase as a high-mass X-ray binary or potential double compact object progenitor. The surviving normal star continues evolving. Eventually, it too will exhaust its fuel and explode. If it's massive enough, it leaves another compact remnant. The system becomes a double neutron star binary, or black hole neutron star binary, or double black hole binary, depending on the masses involved. These double compact object binaries emit gravitational waves, gradually spiraling together over millions or billions of years before finally merging in a cataclysmic collision. Now let's consider binaries containing white dwarfs in more detail. White dwarfs form from stars that aren't massive enough to explode as supernovae. Stars up to about 8 solar masses end their lives more gently. After exhausting their core hydrogen, they fuse helium into carbon and oxygen. But the temperatures needed to fuse carbon are never reached in these stars. The core, now composed primarily of carbon and oxygen, can no longer generate energy through fusion. It contracts until electron degeneracy pressure halts the collapse. The star's outer hydrogen and helium layers are puffed away in stellar winds, forming a beautiful planetary nebula. The core remains as a white dwarf. If this occurs in a binary system, the result depends critically on the orbital separation. In a wide binary, the mass loss during the red giant and planetary nebula phases may have little effect on the companion. The white dwarf and its companion continue orbiting much as before, though the orbit may widen slightly due to the mass loss. In a closer binary, the red giant phase brings the star's surface to or beyond its Roche lobe. Mass transfer occurs, possibly dramatically. The common envelope phase may engulf both stars, and the outcome depends on whether the envelope can be ejected before the cores merge. If the white dwarf and companion survive, as a close binary, the system enters a new phase. The white dwarf is now tiny and dense, about the size of Earth, but containing a solar mass. Its companion may still be on the main sequence, or may itself evolve into a giant. When the companion fills its Roche lobe, mass streams onto the white dwarf. Because the white dwarf is so compact, the accretion luminosity can be enormous. The infalling gas releases gravitational potential energy, heating the accretion disk to tens of thousands of degrees. The inner disk glows brilliantly in ultraviolet light. The hydrogen gas accumulating on the white dwarf's surface is compressed by the white dwarf's intense gravity. The pressure and temperature rise until the hydrogen layer becomes degenerate. In degenerate matter, pressure doesn't depend on temperature, which eliminates the usual thermostatic control in normal stars, where increased fusion rate causes expansion and cooling that regulates the reaction. In the degenerate hydrogen layer, fusion can run away, accelerating explosively. The entire accumulated layer detonates in a thermonuclear runaway, blasting away from the white dwarf at thousands of kilometers per second. This is a nova, brightening the system by factors of 10,000 or more. The nova doesn't destroy the white dwarf. After the outburst, the white dwarf remains, and mass transfer from the companion eventually resumes. The cycle repeats: accretion, accumulation, runaway fusion, nova. Some systems undergo nova, outbursts every few decades or centuries. Others may take thousands of years between events. The recurrence time depends on the mass transfer rate, the white dwarf's mass, and its surface temperature and composition. If the white dwarf is close to the Chandrasekhar limit, around 1.4 solar masses, continued accretion can push it over this threshold. The white dwarf's fate then depends on subtle details of its composition and the accretion rate. For carbon-oxygen white dwarfs accreting at certain rates, the accumulated material can trigger carbon fusion. Unlike the hydrogen fusion in novae, which occurs in a thin surface layer, carbon fusion occurs throughout the white dwarf's interior. The fusion propagates as a detonation wave, traveling through the star at supersonic speeds. In a fraction of a second, the entire white dwarf is consumed by runaway fusion, converting carbon and oxygen into iron group elements and releasing catastrophic energy. The white dwarf is completely destroyed, blown to pieces in a Type Ia supernova. Type Ia supernovae are crucial for cosmology. Their peak brightness is remarkably consistent, with an intrinsic scatter of only about 25% that can be further reduced by applying corrections based on the supernova's light curve shape and color. This makes them excellent standard candles by observing Type Ia supernovae in distant galaxies and comparing their apparent brightnesses to their known intrinsic brightnesses. Astronomers can calculate the distances to those galaxies with good precision. This technique has been instrumental in discovering that the universe's expansion is accelerating, driven by mysterious dark energy. The progenitor systems of Type Ia supernovae remain somewhat uncertain. The white dwarf must accrete enough mass to exceed the Chandrasekhar limit, but there are different ways this could happen. The classical scenario involves a white dwarf accreting from a normal companion star, as just described, but there's also the double degenerate scenario, where two white dwarfs in a binary system spiral together due to gravitational wave emission and merge. If the combined mass exceeds the Chandrasekhar limit, the merger could trigger a Type Ia supernova. Observations of Type Ia supernovae and their remnants are providing clues about which scenario dominates, but the answer may be that both pathways contribute. Let's turn our attention to the exotic physics occurring in the innermost regions of accretion disks around compact objects. As material spirals inward toward a white dwarf, neutron star, or black hole, it reaches velocities approaching the speed of light. At these speeds, relativistic effects become important. Time dilation, length contraction, and the warping of space-time all play roles in determining the disk's structure and the radiation it emits. For a white dwarf, relativistic effects are modest but measurable. The orbital velocity of material in the inner disk, just above the white dwarf's surface, may be a few percent of light speed. This produces small but detectable relativistic corrections to the observed spectrum. For neutron stars, the effects are much stronger. Material orbiting just above a neutron star's surface moves at about 30 to 40% of light speed. General relativity significantly affects the disk's structure. The innermost stable circular orbit, the closest distance at which material can orbit without spiraling inward, is determined by general relativity rather than Newtonian gravity. For a non-rotating neutron star, this innermost stable orbit is at about 3 times the neutron star's radius, or roughly 30 kilometers from the center. For black holes, relativistic effects dominate completely. The event horizon, the boundary of the black hole, is the ultimate inner edge. No material can orbit stably inside, about 3 Schwarzschild radii for a non-rotating black hole, or even closer for a rotating black hole. The Schwarzschild radius, the size of the event horizon, is about 3 kilometers for a solar mass black hole, and scales linearly with mass. Material spiraling into a black hole from the innermost stable orbit releases the maximum possible energy from accretion. Up to about 6% of the rest mass energy can be extracted for a non-rotating black hole, and up to 42% for a maximally rotating black hole. This energy extraction mechanism is extraordinarily efficient, far more so than nuclear fusion. Fusion converts less than 1% of mass into energy, Accretion onto black holes can be 10 or even 40 times more efficient. This is why quasars, powered by supermassive black holes accreting material in the centers of galaxies, can outshine entire galaxies, despite the black hole itself being relatively small. The radiation from accretion disks is not isotropic. The disk emits most strongly from its face, perpendicular to the orbital plane. Emission from the edge of the disk is much weaker. This creates viewing angle effects. An accretion disk, seen face-on, appears brighter than one seen edge-on. For X-ray binaries, this means the observed X-ray flux depends on the orbital inclination. Systems seen edge-on may show dramatic variations in X-ray brightness as the companion star eclipses the disk and the compact object during each orbit. Jets are another dramatic feature of accreting systems. In some X-ray binaries and in many quasars, narrow jets of plasma shoot out perpendicular to the accretion disk at velocities close to the speed of light. These jets can extend for thousands or even millions of light years in the case of quasars. The mechanism that launches jets is not fully understood, but it involves the black hole's spin and the magnetic fields threading the accretion disk. As the disk rotates, it winds up the magnetic field lines. The field lines can become twisted and helical, channeling plasma along them and accelerating it to enormous speeds. The jets carry away energy and angular momentum from the system, affecting the disk's evolution and the black hole's spin. The magnetic fields in accretion disks are generated by dynamo processes similar to the magnetic field generation in stars and planets. Moving, electrically conducting plasma generates magnetic fields, and the differential rotation in the disk amplifies and sustains these fields. The resulting magnetic turbulence is crucial for the disk's operation. It provides the viscosity that allows material to lose angular momentum and spiral inward. Without magnetic turbulence, accretion would be much slower or might not occur at all. Now let's explore the long-term evolution of binary systems and the various endpoints they can reach. The ultimate fate of a binary depends on many factors: the initial masses of the stars, their separation, the metallicity of the gas from which they formed, and the efficiency of mass and angular momentum loss during various evolutionary phases. For wide binaries, where the stars never interact significantly, each star evolves essentially as a single star would. Both stars eventually become white dwarfs, neutron stars, or black holes depending on their masses, but these remnants remain in a wide orbit with little further evolution. Such systems can persist indefinitely, gradually widening as they lose energy to gravitational waves, but on timescales far longer than the current age of the universe. For closer binaries, interactions are inevitable. Mass transfer episodes shape the evolution of both stars. The first mass transfer, occurring when the initially more massive star evolves and fills its Roche lobe, typically leaves the mass donor as a helium star or white dwarf, while the mass gainer is rejuvenated. Later, the second star evolves and may transfer mass back to the remnant of the first star. This leads to complex sequences of mass exchange that can recycle material between the stars multiple times. One important endpoint is a double white dwarf binary. These systems form when both stars are not massive enough to explode as supernovae. Each star goes through the red giant phase, possibly transferring mass, and eventually becomes a white dwarf. The result is two white dwarfs orbiting each other. If the orbit is tight enough, gravitational wave emission will eventually bring them together. The merger of two white dwarfs can lead to several outcomes depending on the total mass. If the combined mass is below the Chandrasekhar limit, the merger might form a single, more massive white dwarf, or if one white dwarf is much less massive, it might be tidally disrupted and form an accretion disk around the more massive one. If the combined mass exceeds the Chandrasekhar limit, a type Ia supernova may result. Binary neutron star systems, as we've discussed, eventually merge due to gravitational wave emission. The merger timescale depends on the orbital period. Very tight binaries merge in just millions of years. Wider binaries may take billions of years or longer. The merger itself is catastrophic, producing gravitational waves, a short gamma-ray burst, and a kilonova from the radioactive decay of heavy elements synthesized in the merger ejecta. The final remnant is either a massive neutron star, or if the total mass exceeds the maximum mass a neutron star can support, a black hole. Black hole binaries represent the most extreme endpoint. Two black holes in a binary orbit emit gravitational waves until they merge. The merger produces a larger black hole and radiates away a substantial fraction of the total mass as gravitational wave energy. The final black hole rings like a struck bell, emitting gravitational waves at characteristic frequencies determined by its mass and spin. These ring-down waves last only a fraction of a second, but provide a direct test of general relativity's predictions for black hole properties. Mixed compact object binaries containing a neutron star and a black hole, or a white dwarf and a neutron star, have their own evolutionary pathways. White dwarf neutron star binaries can accrete material from the white dwarf onto the neutron star, creating X-ray emission and possibly recycling the neutron star into a millisecond pulsar. Neutron star black hole binaries eventually merge, with the neutron star being tidally disrupted and swallowed by the black hole. If the black hole is not rotating rapidly, or if it's too massive relative to the neutron star, the disruption may occur inside the event horizon, producing no electromagnetic counterpart. But if conditions are right, the disruption outside the horizon could produce a burst of electromagnetic radiation. The time evolution of binaries is punctuated by dramatic events: novae, supernovae, common envelope phases, mergers. Between these events, the systems evolve more quietly, gradually changing as the stars age, and orbital angular momentum is lost through various mechanisms. Magnetic braking, where the stellar wind from a magnetic star carries away angular momentum, can shrink the orbit over time. Gravitational wave emission provides another mechanism for angular momentum loss, though it's only significant for very tight binaries. Let's zoom in on some specific examples of unusual binary systems that stretch our understanding. SS433 is one of the most bizarre X-ray binaries known. It consists of a massive star, possibly a supergiant, donating material to a compact object, either a neutron star or black hole. What makes SS433 extraordinary is its jets. The system launches two jets of material moving at 26% of light speed. These jets precess, wobbling around like a spinning top, completing one precession cycle every 162 days. As the jets precess, they trace out a corkscrew pattern in space. The jets are visible at multiple wavelengths, from radio to X-ray, and their Doppler-shifted emission lines create moving features in the system's spectrum. SS433 provides a unique laboratory for studying relativistic jets and precession dynamics. V404 Cygni is a black hole binary about 7,800 light-years away. It undergoes outbursts every few decades when material in the accretion disk becomes unstable and rapidly falls onto the black hole. During these outbursts, the system brightens dramatically in X-rays. The 2015 outburst was particularly well observed, revealing rapid variability and dramatic changes in the X-ray spectrum on timescales of seconds to hours. The black hole's rapid spin and the disk's variable accretion rate create a chaotic environment where relativistic effects are clearly visible. V404 Cygni is teaching us about black hole accretion in the high variability regime. Air Scorpii is a white dwarf binary unlike any other. The system contains a white dwarf spinning once every 1.97 minutes, making it one of the fastest spinning white dwarfs known. The white dwarf has a powerful magnetic field, and as it spins, this field sweeps across the red dwarf companion star. The interaction between the white dwarf's magnetic field and the companion's atmosphere accelerates electrons to high energies, producing synchrotron radiation that pulsates at the white dwarf's spin period. The system pulsates across the electromagnetic spectrum, from radio waves to X-rays. It's the first discovered white dwarf pulsar, showing that white dwarfs can produce pulsar-like behavior without needing to be neutron stars. PSR J1's SM48 to R 2446 AD holds the record for the fastest known rotating neutron star, spinning 716 times per second. It's a millisecond pulsar, a neutron star that has been spun up to extreme rotation rates by accreting material from a binary companion. The material falling onto the neutron star carries angular momentum, spinning it up like a cosmic flywheel. Once the accretion ceases, the neutron star continues spinning at this high rate, emitting radio pulses with extraordinary regularity. Millisecond pulsars are some of the most precise clocks in nature, with rotation periods stable to better than 1 part in a billion over years. This makes them valuable for gravitational wave detection through pulsar timing arrays and for testing fundamental physics. Let's discuss the role of binary stars in nucleosynthesis, the production of chemical elements. Stars are the factories where most elements are made. Hydrogen and helium, the lightest elements, were created in the Big Bang. But all elements heavier than helium are synthesized in stars through nuclear fusion and other processes. Binary interactions significantly affect how and where these elements are produced. In normal stellar evolution, stars fuse hydrogen into helium in their cores. When core hydrogen is exhausted, stars can fuse helium into carbon and oxygen. More massive stars continue to heavier elements: neon, magnesium, silicon, sulfur, and ultimately iron. Each fusion stage releases energy, supporting the star against gravitational collapse. But fusion stops at iron. Fusing elements heavier than iron requires energy input rather than releasing energy. Iron is the end of the line for fusion-powered nucleosynthesis. Elements heavier than iron are made through neutron capture processes. When neutrons are added to atomic nuclei, heavier isotopes and eventually heavier elements are created. There are 2 main neutron capture processes. The slow process, or S process, occurs in the helium-burning shells of red giant stars. Neutrons are produced as byproducts of helium fusion and are slowly captured by seed nuclei, building up heavier elements over thousands of years. The S process produces about half of the elements heavier than iron. The rapid process, or R process, occurs in environments with extremely high neutron densities, so high that nuclei can capture multiple neutrons before radioactive decay occurs. The R process builds up very neutron-rich isotopes that subsequently decay, producing the stable heavy elements we observe. The R process creates the other half of heavy elements, including gold, platinum, uranium, and many others. For decades, the astrophysical sites where the R process occurs were uncertain. Supernova explosions were long suspected, but detailed models showed that most supernovae don't produce the right conditions. Binary neutron star mergers provide the answer. The neutron-rich material ejected during the merger undergoes intense R process nucleosynthesis, creating heavy elements in quantities matching what we observe in the universe. The 2017 observation of GW1 Sensven 817, the binary neutron star merger, confirmed this. The electromagnetic counterpart, the kilonova, showed spectroscopic signatures consistent with massive amounts of R process elements being synthesized. Current estimates suggest that a single binary neutron star merger can produce several Earth masses of gold and platinum, along with much larger quantities of other heavy elements. Binary systems containing white dwarfs also contribute to nucleosynthesis. Type Ia supernovae, resulting from white dwarf binary evolution, produce copious amounts of iron, nickel, and related elements. These supernovae are major sources of iron in the universe. Without type Ia supernovae from binary systems, the universe would have far less iron and related elements. This would affect not just stellar compositions, but also planet formation. Rocky planets like Earth are built from heavy elements. A universe with fewer binary stars would have fewer type Ia supernovae and thus less iron, potentially reducing the frequency of terrestrial planets. Novae, though less energetic than supernovae, also contribute to the chemical enrichment of the galaxy. Each nova explosion ejects material enriched with elements produced during the outburst. While the total amount per nova is modest, the high frequency of novae occurring throughout the galaxy continuously means they collectively contribute significantly to certain isotopes. Now let's examine how astronomers observe and analyze binary stars in practice. The techniques vary depending on the type of binary and the information sought. For visual binaries, direct imaging is the primary method. Large telescopes equipped with adaptive optics or interferometry can resolve the two stars and measure their separation and position angle over time. Repeating these measurements at multiple epochs builds up the orbital motion. Fitting an elliptical orbit to these data points allows determination of the orbital parameters. Spectroscopy is essential for spectroscopic binaries and for obtaining detailed information about the stars in any binary. High-resolution spectrographs spread the starlight into thousands or tens of thousands of wavelength channels, revealing the detailed shapes of spectral lines. For double-lined spectroscopic binaries, cross-correlation techniques can separate the two stellar spectra and measure the radial velocities of each star independently. The Doppler shifts are typically measured to precisions of tens of meters per second or better with modern spectrographs. These precise velocities, combined with the orbital period, yield the mass function and can determine masses if the inclination is known. Photometry, the measurement of brightness over time, is crucial for eclipsing binaries and for detecting transiting circumbinary planets. Modern photometers can measure stellar brightnesses to precisions of a few parts per million, enabling detection of shallow eclipses and small planetary transits. Space-based photometry from missions like Kepler-TESS and COROT provides continuous, high-precision light curves free from atmospheric interference. These light curves, covering days to years, reveal not just eclipses but also stellar variability, orbital modulations due to ellipsoidal distortion or reflection, and other subtle effects. Interferometry combines light from multiple telescopes to achieve angular resolutions far exceeding what any single telescope can attain. The Very Large Telescope Interferometer in Chile and the Cara Array in California have resolved binary stars with separations of just a few milliarseconds. They've measured the sizes of stars, observed the shapes of tidally distorted stars in close binaries, and directly imaged accretion disks. Interferometry provides spatial resolution complementary to spectroscopic and photometric observations. Gravitational wave detectors are now the primary means of observing compact object binaries in their final moments. LIGO and Virgo use laser interferometry to measure the tiny stretching and squeezing of space-time caused by passing gravitational waves. The detectors are exquisitely sensitive, capable of measuring length changes smaller than the diameter of a proton over distances of several kilometers. When a gravitational wave passes through, the detector's arms alternately stretch and compress, creating a characteristic signal. Signal processing algorithms search through the detector noise to identify gravitational wave events and extract their properties. Combining observations across multiple wavelengths and using multiple techniques provides the most complete picture of binary systems. For instance, observing an X-ray binary with optical spectroscopy to measure radial velocities, X-ray satellites to study the accretion disk and compact object, and radio telescopes to detect jets yields a comprehensive understanding unattainable with any single technique alone. This multi-wavelength approach has become standard in modern astrophysics. Let's consider the statistics and demographics of binary systems. How common are binaries among different stellar populations? What are the typical orbital periods and mass ratios? These questions have fundamental importance for understanding star formation and galactic evolution. Surveys over the past decades have built up large samples of binary stars, allowing statistical analysis for solar-type stars, stars with masses between about 0.8 and 1.2 solar masses. The binary fraction is approximately 40 to 50%. This means that roughly half of Sun-like stars have companions. The distribution of orbital periods is broad, extending from a few hours for contact binaries up to millions of years for the widest pairs. There's a peak in the distribution around orbital periods of 100 to 300 years, corresponding to separations of about 30 to 100 astronomical units. Very short period and very long period binaries are less common, though selection effects make it harder to detect these extremes. For more massive stars, the binary fraction increases. B-type stars, with masses around 3 to 10 solar masses, have binary fractions of 60 to 70% or higher. O-type stars, the most massive stars with masses above 10 solar masses, are almost all in binary or multiple systems. The high binary fraction for massive stars may reflect their formation in dense turbulent regions where fragmentation readily produces multiple systems. For low-mass stars, the binary fraction decreases. M dwarfs, red dwarfs with masses less than 0.5 solar masses, have binary fractions around 20 to 30%. Brown dwarfs, substellar objects, below about 0.08 solar masses that never ignite stable hydrogen fusion, rarely have companions. The decreasing binary fraction toward lower masses suggests that the fragmentation process is less efficient at small mass scales, or that low-mass binaries are more easily disrupted during the star formation process. The distribution of mass ratios, the ratio of the less massive to the more massive star, also varies with stellar mass and orbital period. For wide binaries, the mass ratio distribution is relatively flat, meaning all mass ratios from very unequal, mass ratio near 0, to nearly equal, mass ratio near 1, are comparably common. For closer binaries, there's a preference for more equal mass ratios, with a peak near mass ratio of 1. This might reflect preferential formation of equal mass pairs during disk fragmentation or survival bias, where unequal mass close binaries are more likely to merge during common envelope evolution. These demographic patterns provide constraints on star formation theories and binary evolution models. Simulations of star formation must reproduce the observed binary fractions, period distributions, and mass ratio distributions. Comparing simulations to observations helps refine our understanding of the physical processes operating in star-forming regions. In conclusion, binary stars are not just common features of the galaxy, but fundamental components of stellar populations and galactic evolution. They provide unique laboratories for measuring stellar properties and testing physical theories in regimes inaccessible with single stars. They generate some of the most spectacular phenomena in the universe, from novae to supernovae to gravitational wave events. They complicate planet formation, but also create environments where exotic forms of habitability might arise. Understanding binary stars is essential for understanding the universe. We've journeyed through the formation of binary systems, from fragmenting molecular clouds, explored the intricate orbital mechanics that bind them together, examined the diverse ways they reveal themselves to our telescopes, and witnessed the dramatic transformations that occur when stars in close pairs interact. We've seen how mass transfer reshapes stellar evolution, how compact objects create high-energy fireworks in X-ray binaries, and how the ultimate mergers of neutron stars and black holes ripple through space-time as gravitational waves. We've met famous binary systems from Sirius to Cygnus X1, each teaching us something unique about stellar physics. And we've discovered that even planets can orbit binary stars, experiencing double sunsets on worlds we're only beginning to understand. The study of binary stars connects virtually every field of astronomy. It links star formation with stellar evolution, galactic dynamics with gravitational wave physics, chemical evolution with planet formation. Binary systems demonstrate that the universe's complexity emerges from the interplay of simple physical laws applied in different configurations. Gravity, thermodynamics, nuclear physics, quantum mechanics, and relativity all contribute to the rich phenomenology we observe. Looking to the future, our understanding of binary stars will continue deepening. Gaia will complete its mission with a comprehensive census of the Milky Way's binary population. LIGO, Virgo, and future gravitational wave detectors will observe thousands of compact object mergers, mapping out the population of binary black holes and neutron stars across cosmic history. The James Webb Space Telescope and future extremely large ground-based telescopes will study circumbinary planets and protoplanetary disks around young binaries, revealing how planets form in these complex environments. New theoretical models, powered by ever more capable supercomputers, will simulate binary evolution and stellar interactions with increasing fidelity. The history of binary star observations reflects the broader history of astronomical instrumentation and technique. Each new generation of telescopes and detectors revealed binary systems that previous technology couldn't detect, expanding our census of these systems and our understanding of their properties. Let's trace this observational history in more detail, seeing how the field evolved alongside technological progress. The earliest binary star observations relied entirely on visual detection with telescopes. In the 1600s and 1700s, telescopes were small and optically imperfect, but they were sufficient to reveal some of the wider binary pairs. Mazar's discovery in 1617 showed that even early telescopes could split doubles that appeared single to the naked eye. As telescope apertures increased throughout the 1700s, more binaries were discovered. Larger apertures provide better angular resolution, allowing separation of closer pairs. The relationship between telescope aperture and angular resolution is governed by the physics of diffraction. Light passing through a circular aperture produces a diffraction pattern with a bright central spot surrounded by fainter rings. The angular size of this central spot, called the Airy disk, determines the smallest angular separation the telescope can resolve. The Airy disk's diameter is approximately 1.22 times the wavelength of light divided by the telescope's diameter. For visible light, wavelength around 500 nanometers, and a 10-centimeter telescope, the Airy disk is about 1.2 arcseconds across. Increasing the telescope to 1 meter diameter shrinks the Airy disk to 0.12 arcseconds. This is the diffraction limit. In practice, Earth's atmosphere limits ground-based telescopes' resolution more severely than diffraction. Turbulence in the atmosphere causes the light from stars to shimmer and dance, blurring their images. The typical atmospheric seeing, the angular size of a star's blurred image, is around 0.5 to 2 arcseconds at good observing sites. This means even very large telescopes with diffraction limits of 0.1 arcseconds, or better, are limited to 0.5 arcsecond resolution by atmospheric blurring. Astronomers developed techniques to combat atmospheric seeing. In the late 1900s, adaptive optics systems became practical. These systems use deformable mirrors that can change shape hundreds or thousands of times per second to compensate for atmospheric distortions. A bright reference star or a laser-generated artificial star provides real-time information about the atmospheric turbulence. The adaptive optics system measures the distortions and adjusts the mirror's shape to cancel them out. The result approaches diffraction-limited resolution. Modern large telescopes with adaptive optics can achieve resolutions of 0.05 arcseconds, or better, revealing binary stars with separations impossible to detect before. Space-based observations avoid atmospheric blurring entirely. The Hubble Space Telescope, operating above the atmosphere since 1990, routinely achieves its diffraction limit of about 0.05 arcseconds at visible wavelengths. This has allowed Hubble to resolve binaries invisible from the ground and to measure orbital motions with unprecedented precision. The upcoming James Webb Space Telescope, though primarily designed for infrared observations of distant galaxies, will also provide extraordinary resolution for studying binary stars, particularly in infrared wavelengths, where many cool stars and dusty environments are best observed. Spectroscopy revolutionized binary star studies in the late 1800s. When starlight is spread into a spectrum, it reveals dark absorption lines at specific wavelengths corresponding to the atoms and molecules in the star's atmosphere. These lines act like fingerprints, identifying elements and revealing temperature, pressure, and chemical composition. For binary stars, spectroscopy added a powerful new dimension. The Doppler effect, discovered in the 1840s, states that waves from a moving source are shifted in wavelength. For light, sources moving toward us are blue shifted to shorter wavelengths, while sources moving away are red shifted to longer wavelengths. The shift is proportional to the velocity along the line of sight. By measuring the wavelength shifts of spectral lines, astronomers can determine radial velocities with great precision. In a spectroscopic binary, the stars are too close to resolve visually, but their spectral lines shift back and forth as they orbit. When both stars contribute detectable spectral lines, the spectrum shows two sets of lines shifting in opposite directions. At some orbital phases, one set of lines is blue shifted, while the other is red shifted. Half an orbit later, the shifts reverse. The amplitude of these shifts depends on the star's orbital velocities, which in turn depend on the stellar masses and orbital size. Early spectroscopy used photographic plates to record spectra. Astronomers would attach a spectrograph to a telescope, directing starlight through a prism or diffraction grating that spread it into a spectrum, then exposing a photographic plate to record the spectrum. This process required long exposures, often many hours for faint stars, during which the telescope had to track the star precisely. The photographic plates were then developed and measured carefully to determine the wavelengths of spectral lines. This labor-intensive process limited the number of stars that could be studied and the precision achievable. Modern spectroscopy uses electronic detectors, primarily charge-coupled devices or CCDs. These are far more sensitive than photographic plates, requiring much shorter exposures. They also provide digital output that can be analyzed by computers, eliminating the tedious manual measurements of photographic plates. High-resolution spectrographs combined with large telescopes and CCD detectors can measure radial velocities to precisions of 1 meter per second or better. This incredible precision enables detection of planets around other stars through the tiny wobbles they induce in their host stars, with amplitudes of just a few meters per second for Earth mass, planets in Earth-like orbits. Photometry, the measurement of brightness, evolved in parallel with spectroscopy. Early photometric observations used the human eye as detector, with observers estimating brightnesses by comparison to nearby stars. This was surprisingly effective for detecting brightness variations in eclipsing binaries and other variable stars. Observers developed standardized magnitude scales and comparison star sequences that allowed systematic monitoring of variable stars. Dedicated observers compiled light curves showing how a star's brightness changed over time, revealing eclipse patterns and other variability. Photoelectric photometry, introduced in the mid-1900s, used photomultiplier tubes to convert light into electrical current that could be measured precisely. This was far more accurate than visual estimates and could detect fainter stars. Photomultiplier tubes dominated astronomical photometry for decades, allowing precise measurements of eclipse depths, orbital phase variations, and stellar pulsations. CCD photometry, beginning in the 1980s, brought another revolution. CCDs could image large areas of sky simultaneously, measuring brightnesses of many stars in a single exposure. This enabled systematic surveys of star clusters and galaxies, searching for variable stars and eclipsing binaries. Automated pipelines could process thousands of images, identifying variables and measuring light curves with minimal human intervention. Ground-based survey projects like the Optical Gravitational Lensing Experiment and the All-Sky Automated Survey monitored millions of stars, discovering countless eclipsing binaries and other variables. Space-based photometry reached new heights with the Kepler mission, launched in 2009. Kepler monitored over 150,000 stars continuously for 4 years, measuring their brightnesses every 30 minutes with precision of a few parts per million. This unprecedented dataset revolutionized exoplanet science, discovering thousands of planets through their transits. It also provided extraordinary data for studying eclipsing binaries, detecting subtle effects like orbital ellipsoidal variations, reflected light, and even star spots on the surfaces of binary components. The TESS mission, launched in 2018, is conducting an all-sky survey with similar photometric precision, extending these studies to bright stars across the entire sky. Interferometry represents another frontier in binary star observations. By combining light from multiple telescopes separated by large distances, interferometry achieves angular resolution far exceeding what any single telescope can attain. The resolution of an interferometer depends on the separation between telescopes, called the baseline, rather than the size of individual telescope apertures. A baseline of 100 meters provides resolution of about 0.001 arcseconds at visible wavelengths, allowing extremely tight binaries to be resolved. The Navy prototype optical interferometer, located in Arizona, uses multiple telescopes on baselines up to 400 meters. It has directly imaged the components of spectroscopic binaries, measuring their sizes and separations with milliarcsecond precision. The Very Large Telescope Interferometer combines light from the 4 8-meter VLT telescopes, achieving resolutions better than 0.001 arcseconds. It has resolved accretion disks around compact objects and measured the oblateness of rapidly rotating stars in close binaries. Radio interferometry, using arrays of radio telescopes, provides even finer angular resolution. The Very Long Baseline Array uses 10 radio telescopes spread across the United States and its territories, with baselines up to 8,000 kilometers. This yields angular resolutions of about 0.001 arcseconds, sufficient to resolve structure in jets from X-ray binaries, and to precisely measure positions of radio-emitting binaries. The Event Horizon Telescope, a global array of radio telescopes, achieves resolutions of about 0.0002 arcseconds, enough to image the event horizons of supermassive black holes, and potentially to study accretion flows in stellar mass black hole binaries. Astrometry, the precise measurement of stellar positions, has a long history in astronomy. Early astrometry used specialized instruments like meridian circles to measure star positions relative to reference grids. These measurements had precisions of about 0.1 arcseconds, sufficient to detect the proper motions of nearby stars and the wobbles induced by massive planets or stellar companions. The Hipparcos satellite, operating from 1989 to 1993, measured positions of over 100,000 stars with precisions of about 1 millisecond. This revealed astrometric binaries and measured parallaxes that gave direct distances to thousands of stars. Gaia, Hipparcos' successor, is measuring positions, parallaxes, and proper motions for over 1 billion stars with microarc-second precision. For bright stars, Gaia achieves precisions better than 10 microarc-seconds, revealing tiny wobbles from planetary companions and refining orbits of binary stars. Gaia's data is transforming our understanding of the Milky Way's structure, stellar populations, and binary demographics. The mission will operate through at least 2025, and its final catalog will provide the definitive reference for stellar positions and motions. Let's turn our attention to the computational methods used to analyze binary star observations. Extracting the physical parameters of a binary from observational data requires solving complex inverse problems. For eclipsing binaries, observers have light curves showing brightness variations. These must be converted into stellar radii, temperatures, orbital inclination, and other parameters. This is done through light curve modeling. Light curve modeling uses detailed physical models of binary star systems. The models account for the star's shapes, which can be distorted by tidal forces and rotation. They include limb darkening, the dimming toward the edges of stellar disks, due to viewing through different depths of the stellar atmosphere. They incorporate reflection effects, where light from one star illuminates the facing hemisphere of its companion. And they calculate how much light is blocked during eclipses based on the orbital geometry and stellar sizes. The Wilson-Devaney code, developed in the 1970s and continuously refined since, is the standard tool for light curve modeling. It solves the equations for binary star configuration, accounting for all the physical effects mentioned above, and generates synthetic light curves that can be compared to observations. By adjusting the model parameters and searching for the best fit to the data, astronomers can determine the stellar properties with remarkable precision. Modern implementations use sophisticated optimization algorithms and Bayesian inference techniques to explore the parameter space efficiently and to estimate uncertainties in the derived parameters. For spectroscopic binaries, radial velocity modeling is the key analysis technique. Observers have radial velocity measurements at different orbital phases. These must be converted into orbital parameters and stellar masses. If only one star's spectrum is visible, the mass function can be calculated, but the individual masses remain uncertain due to the unknown inclination. If both stars' spectra are visible, the mass ratio can be determined from the amplitude ratio of their radial velocity curves. If the binary is also eclipsing, the inclination is known, and the complete orbital solution, including individual masses, can be obtained. Orbital fitting involves comparing observed radial velocities to model predictions based on Keplerian orbits. For circular orbits, the radial velocity varies sinusoidally with time. For eccentric orbits, the variation is more complex, with the shape depending on the eccentricity and the orientation of the orbit's long axis. Least squares fitting, or Markov chain Monte Carlo methods, are used to find the orbital parameters that best match the observations and to quantify the uncertainties. For visual binaries, orbital fitting uses the measured positions of one star relative to the other at different times. These positions trace out an ellipse on the sky, but this is the projection of the true three-dimensional orbit onto the plane of the sky. Transforming from the observed apparent orbit to the true orbit requires determining the orbital inclination and the orientation of the orbital plane. This is done by fitting an ellipse to the observed positions and then using geometric relationships to find the three-dimensional orbital elements. Combining different types of observations provides the most complete solutions. A binary that is both eclipsing and spectroscopic, with radial velocities for both stars, and a well-sampled light curve, can have its parameters determined to percent level precision or better. The masses, radii, temperatures, and luminosities of both stars can all be measured directly. These precisely characterized binaries serve as critical tests of stellar evolution models and as calibrators for stellar parameter estimation techniques. The interpretation of binary star observations also requires careful attention to systematic uncertainties and selection effects. Observations are subject to various biases that can distort our perception of the underlying binary population. For instance, eclipsing binaries are only visible if their orbital planes are nearly edge-on to our line of sight. This means the eclipsing binaries we observe are a small subset of all binaries with similar orbital periods and stellar properties. To infer the true binary population from observed samples, astronomers must correct for this geometric bias, accounting for the fact that we only see binaries with favorable orientations. Similarly, spectroscopic binaries are easier to detect if their orbital velocities are high, which occurs for short period or high mass systems. Long period binaries with small velocity amplitudes may go unnoticed in spectroscopic surveys unless very high precision can be achieved. Visual binaries are easiest to detect if they're nearby, because angular separation on the sky depends on physical separation divided by distance. A binary with 10 AU separation appears 0.1 arcseconds across if it's 100 light-years away, but only 0.1 arcseconds across if it's 1,000 light-years away. This distance bias means our visual binary census is most complete for nearby systems and increasingly incomplete at greater distances. Selection effects also affect which types of binaries are most studied. Bright binaries receive more attention than faint ones, simply because they're easier to observe. Eclipsing binaries are preferentially studied because their light curves provide more information than photometry of non-eclipsing systems. X-ray binaries containing compact objects are intensively observed because they're rare and interesting, while ordinary detached main sequence binaries receive less scrutiny despite being far more common. These observational biases must be accounted for when attempting to understand the full binary star population. Now, let's explore some of the unanswered questions and ongoing debates in binary star research. Despite centuries of study, many aspects of binary stars remain poorly understood or actively controversial. These open questions drive current research and will occupy astronomers for decades to come. One major question concerns the origin of the closest binary systems, those with orbital periods of hours to days. How do stars end up in such tight orbits? These systems likely didn't form with such close separations. Stars forming in such proximity would merge before reaching the main sequence. Instead, close binaries probably formed at wider separations and then had their orbits shrink through some process. Common envelope evolution is the leading candidate for this orbital shrinking, but the details are uncertain. How efficiently is orbital energy transferred to the envelope? What fraction of binaries survive common envelope episodes versus merging? Can orbital angular momentum lost through magnetic braking or gravitational radiation also contribute significantly to orbit shrinkage? The birth rate and evolutionary pathways of compact object binaries remain incompletely understood. LIGO and Virgo have detected dozens of binary black hole mergers, but translating these detections into constraints on the underlying population requires modeling the selection effects and the range of possible evolutionary paths. Do binary black holes form primarily from isolated massive binary evolution, or do they form through dynamical interactions in dense star clusters? What are the typical black hole spin distributions, and what do they tell us about the star's collapse and the binary's formation histories? Different formation channels predict different distributions of masses, spins, and merger rates, but current observations are not yet sufficient to definitively distinguish among these scenarios. The maximum mass of neutron stars is another hotly debated topic. Theoretical calculations suggest neutron stars cannot exceed about 2 to 3 solar masses before collapsing into black holes. The exact limit depends on the equation of state of nuclear matter at extreme densities, which is uncertain. Observations of neutron stars in binary systems provide constraints. The most massive, precisely measured neutron star is PSR J0348+0432, with a mass of about 2.01 solar masses. Gravitational wave event GW198414 involved a compact object with about 2.6 solar masses, which could be either the most massive neutron star or the least massive black hole ever detected. Future observations of more neutron stars, particularly in systems allowing precise mass measurements, will help constrain the maximum mass and thus the properties of ultra-dense matter. The role of magnetic fields in binary evolution is an area of active research. Magnetic fields can transport angular momentum within stars and from stars to their surroundings. In close binaries, magnetic braking, where stellar winds follow magnetic field lines and carry away angular momentum, can shrink orbits over time. The strength of magnetic braking depends on the stellar rotation rate and the magnetic field strength, both of which evolve as the stars age and interact with their companions. Precise models of magnetic braking are needed to predict the orbital evolution of low-mass binaries and the production rates of cataclysmic variables and other interacting systems. The diversity of type Ia supernova properties presents puzzles for binary evolution models. While type Ia supernovae are used as standard candles, they show some intrinsic variation in brightness and spectral properties. Different subclasses have been identified based on light curve shapes and spectra. These variations may reflect differences in the progenitor systems or explosion mechanisms. Are some type Ia supernovae from white dwarfs accreting from non-degenerate companions, while others come from white dwarf mergers? Do the explosion mechanisms vary, with some being pure detonations and others involving deflagration followed by detonation? Answering these questions requires understanding the full range of binary evolution pathways that can lead to type Ia supernovae. The connection between binary stars and gravitational wave sources will continue to deepen. As gravitational wave detectors improve and accumulate more detections, they will provide unprecedented insights into the compact object binary population. Combined observations using gravitational waves and electromagnetic radiation, multi-messenger astronomy, will reveal the environments where binaries merge and the physical or processes occurring. The 2017 observation of GW17087, the binary neutron star merger, was a preview of this future. It combined gravitational waves, gamma rays, optical light, and radio waves to provide a comprehensive picture of the merger event. Future multi-messenger observations will become routine, characterizing mergers in detail and using them to test fundamental physics and cosmology. The study of binary stars connects to the broader question of habitability and the search for life beyond Earth. Binary stars are common, and planets in binary systems are now known to exist. Could life arise on such planets? Would the complex stellar environment with varying radiation levels and potentially unstable climates prevent life's emergence or evolution? Or might binary systems offer unique niches for life, perhaps even enhancing habitability in some configurations? These questions touch on fundamental issues in astrobiology and planetary science. As we discover more circumbinary planets and characterize their atmospheres, we will begin to answer them. In reflecting on our journey through binary star systems, we can appreciate how these celestial pairs embody fundamental principles of physics while simultaneously presenting us with endless variety and complexity. Each binary system is unique, with its own history of formation, evolution, and interaction. Yet they all follow the same physical laws. This combination of diversity within unity is characteristic of the natural world and reflects the deep patterns underlying nature. Binary stars remind us that the universe is interconnected. Stars do not exist in isolation, but interact with their surroundings and with each other. These interactions shape stellar evolution, drive chemical enrichment, produce energetic phenomena visible across vast distances, and create the elements from which planets and life are built. In studying binary stars, we study the machinery of the cosmos, the processes that have crafted the universe we inhabit, and that continue shaping its future. Looking forward, the future of binary star research is bright. New instruments across all wavelengths, from radio to gamma rays, will provide ever more detailed observations. Gravitational wave astronomy will mature from its current infancy into a powerful probe of the universe. Computational capabilities will continue growing, enabling simulations of unprecedented realism and complexity. And new theoretical insights will emerge as we synthesize data from multiple wavelengths and techniques. The story of binary stars is far from complete. Each answer we find raises new questions. Each discovery reveals new complexities. This is the nature of science, an ongoing dialogue with nature, where observation and theory iterate toward ever deeper understanding. Binary stars will continue to be central to this enterprise, providing both laboratories for testing our theories and sources of surprises that challenge our assumptions. Thank you for joining me on this journey through the realm of binary stars. If you found this exploration meaningful, please consider liking and subscribing to the channel. Your support helps me continue making these deep dives into space and our place within it. Until next time, keep looking up at the night sky. Keep wondering about the stars you see. And remember that most of those points of light are not solitary suns, but pairs and multiples. dancing together across the cosmos in gravitational embrace. The universe is richer and more complex than it appears at first glance, filled with hidden relationships and interactions that shape everything we observe. Binary stars embody this complexity, showing us that even in the vast emptiness of space, companionship is the rule rather than the exception. Good night.